it is to find some patterns, right? Some features. So that's what you're doing, features detections. And then after that, you need to find some descriptions or signatures of each key point so that you can find a corresponding point between two images. So that's what we are going to do today, right? In the give me a moment. Oops. Okay. So, like I mentioned, to perform a features matching pipeline, we first have to perform a features detection in which we identify the interest point, and then after that, we are going to do extract some vectors which represents descriptors of uh, uh, an interest point, so that we can use this signature to perform a feature matching, which is we are going to find the correspondent between the two views. So now let's focus on feature descriptions. Okay. So like I mentioned in previous class, this kind of applications has been used in many applications. For example, in object detections or even like template matching, OCR, something like that. All right. So, and also in previous class, we have been discussing how can we detect any objects in a Vivid cluster, a blackout, or any cluster scene. All right. So this brings us to the technique that we can use to both detect the features as well as perform the features descriptors so that we can match the key point between two images, right? So, in these scenarios, we need to find some matches, some interesting points, or what we call features, right? So then, for the technique that we are going to learn today is the SIF, which is scale invariance features transform. So we use this technique to align the image, and also we use the technique to perform the 2D image recognitions. All right. So the topics that we are going to cover today will be first, we will define what is an interest point, which I think we already discussed last week, and also how to detect a blob. What is a blob, and then how can be detected. And then we'll talk about the SIF detectors, and then later on we will discuss about the SIF descriptors. All right. So we already have discussed this one. What is the interest point, right? So the interest point, the point that can be interesting, it might be in different size, different orientations, different lighting conditions, and the brightness. So the interest point, it should be invariance to this kind of variations, right? So the point that we can pick as an interest point, it has to be invariant to these sort of properties. It does not matter that whether the point in one image and then the interest point in two images, it doesn't matter of the size of the lighting condition. It should be the good interest point should be able to allow us to match between the two scenes. So, for example, if we remove these variations, we can match this interest point by, for example, if we are removing the source of variation like scale, we can scale it up and then we can match. And so, for example, in this example, it has a variations of scale and rotations and brightness, right? So this is the original, this is the destination, or the one that we are looking at. So if we removing source of variation, for example, if we removing the scale, so we scale it up to match the original scale, and then we remove the orientations so that if we removing these variations, the matching become easier for us to match the interest point between two scenes, right? So, but this is an example of patches that is not interesting because we cannot find any pattern to match between the two images, right? So, what is a good interesting point, or what are the properties of what we call good features, all right? So the good features has to have a rich image contents, for example, a brightness, a color variations within some certain local windows, right? That's what we call a patch. And then it has to have a well-defined representations, or we call it signatures, so that we can use signatures for matchings or comparing with other points between the two images. All right. So, and also a good features has to have a well-defined positions within the image. So we have to be able to localize that features or that point within the image so that we can use their location to match with another point, which is a corresponding point in another image. All right. And it's also have to be invariant, which means it doesn't it tolerate the rotations and the scaling. And also it has to be insensitive to the lighting change, right? When we are taking the image, so we cannot control to some extent, we cannot control the lighting, so that a good algorithm that we are going to use to detect features, it has to be insensitive to lighting change. All right. So these are the property or the good property of a good feature point. Okay. So the question is the lines and edges can be considered as an interesting point or not? All right. So if we closely look at this example image, we can see that we cannot localize these edges like exactly where it is, because there are multiple edges that are look exactly the same, right? So for example here, because the edges it just are a sequence of pixel, right? That it just a sudden change of brightness between the pixels. So that's what we define edges. So if you look at this, it is very difficult to find the locations of any edges and then identify that there are the same edges between the two images. All right, because if you look at this image, at these edges, we are not sure that whether this point and this point are the same edges or not, because this point, the blue one and the green one, they have this look exactly the same if we look at the features, the edges features. So that it is very unclear, or it is very ambiguous for us to match the one on the left to the one on the right. So we are not certain whether we should match the red one to the blue or to the green one. All right. So edges and lines probably is not a good candidate for being a feature point. And then what about the blob? So the blob is nothing but a certain patch, small local windows within the image. All right. So the blob, it has a property of we can find a fixed positions and a size of the blob. So we can define the size of the blob, or like the local windows that we are interested in, and then we just looking at that particular locations and extract the signatures or the representations of this particular patch, and then we can find the same patches from another image, and then look at the signature, whether they are the same or not. So by using the blob, we can extract more information rather than just using the edges or lines. So so that if we use a blob, we can certainly have their locations, and as well as we can define the size of the blob that we want to pick up as the interesting point. All right. So we'll see later how we can find the blob with different size, and then how we can localize those blob as well. All right. So blob here can be considered as the interesting point, or the point that we can pick up as a candidate to use for a feature matching. All right. So blob as interest point, because we need, so for the blob like features to be useful, we need to be able to locate them. We need to know their locations. We need to be able to determine its size, how large, how small it is. And then we also need to determine the orientations, right? The orientations of the blobs, so that we can also need to be able to formulate the descriptions or the signature. That's what I call the signature here, which is just a vector that represent the characteristic of this particular blobs, right? So the question is what tool that we can use to find this blob with this features or with this characteristic. All right. So what are the tools that can be performed or that we can use to find this blob? So that's bring us to the SIF, right? So this is the SIF can do that. But before we dive into the SIF, let's just review what we have studied in last week. So let's first revisit the Gaussian filters. I hope you guys remember what is the Gaussian filters. So if you look at the image as a one-dimensional signal, right? So the F here as the one-dimensional signal. So as I mentioned, the image can be viewed as functions, right? So here, if we first, before we dive into 2D, let's look at the image as one-dimensional signal, F here. So if we apply a Gaussian filters here, so which is the Gaussian filters. So if we apply the Gaussian filter, which means what we are doing, we are just smoothing out, which removing the noise, so that we can better get a better smooth images. So that's the purpose of applying the Gaussian, right? So that's what Gaussian filter does. And then if we take a derivative of the Gaussians, right? If we take the derivative of the Gaussian over here, we have a Gaussian, and then we take a derivative of that. So what we are getting here, we are getting the signal that is have a crossing, zero crossing like there. All right. So this is another filter that we have. We take a derivative of that Gaussians, and then we apply the derivative of the Gaussians to the image. All right. So we can also removing the noise, and then we can detect an edges, right? So if you want to find the edge within the image, we can use a derivative of the Gaussian to do that. And then if we further take another derivative of that, which is we call a second derivative of the Gaussians, right? If you take a second derivative of the Gaussian, this is what your filter looks like, right? So this is what your filter looks like. And then if you apply these filters to the image, you can detect an edges by identifying a zero crossings, right? By using a derivative of Gaussians to determine the locations of the edge, you just need to find the peak of the result. So wherever the peak, that is where the edge is. All right. But if you apply the second derivative of the Gaussians, we can localize, or we can determine the edge by finding the zero crossing positions, right? So that's how you can find the edges by using second derivative of the Gaussians, right? So so that's when we look at the image as a one-dimensional signal, right? So now let's look at the blobs, 1D blob first, and then we will discuss about 2D blobs later. For simplicity, we first look at the 1D blob. So here are the example of 1D blob like, right? Before we're talking about the 2D. So this is what we call a blob in one dimensionals or 1D signal. So blob can have many shape, rounded, rectangle, or this like triangle, something like that, all right, or hemisphere, something like that. So this is what we call a blob, right? So let's take a look at the first one for simple example. So let's say that we have the signal fx, right? And then we have three blob A, blob B, and blob C. And then the blob B has a width which is twice as the width of the blob A. And the blob C, the width of the blob C is 3 times the width of the blob A. All right. So in order to detect the edges or the peak at each, so we want to detect each blob, right? So we want to detect each blob. So if we apply, if we have these Gaussians, right? If you have these Gaussians, and then we have we taking the second derivative of this Gaussian. So this is what the signal that we got, right? Or the filter. This filter gonna look something like this for this particular Gaussians with some sigma value. Okay. So the sigma value, to recap here, the sigma value, it just control the width of the Gaussian, right? The control the width over here. Let me just write something. So for the Gaussians, the sigma, if you define the sigma, it will control the width of this Gaussian filters, right? So which means if you change the value of sigma, if you increase the value of sigma, the Gaussian filter would look something like this, which is it has a wider base over here, right? So that's the sigma. So if we take a second derivative of that, second derivative of that Gaussians, the above one, so this is what you get. This is how your filter looks like, okay? And if you apply the second derivative to the blob over here, to the blob over here, all right, to the blob over here. So this is what you got. This is a result of applying second derivative of the Gaussians to the blob, this is the output. And if you take the sigma square and then multiply with the second derivative of Gaussian, what we end up with is the normalized output. Right. So this is what we call a sigma normalized output. So what does this tell us? So if we keep changing the Gaussian, right? If we keep changing the value sigma of the Gaussians, the peak, if the sigma of the Gaussian getting wider, the peak values of the output will be decreased. All right, so let's take an example. Let me give you a demo of this one, so you better visualize this. So for example, look at this. So what we want to do here is that we want to detect each blob, right? We want to detect the blob. So first, our task is to detect the blob, okay? To detect the blob. So previously we detect an edge, but now we want to use a filters or Gaussians, derivative of Gaussian, second derivative of Gaussian to detect the blob, okay? So here is the Gaussian signal. Here's the Gaussian signals. And then if you apply these filters, Gaussian, with this sigma is equal to 2.5, all right? If you apply this, and then you take a second derivative of this Gaussian, which is a Laplacian of Gaussian. So this is what you get as a filters, all right? This is your filters, okay? And then you convolve this filter with each and every blob over here. You convolve this, the black one over here, with the blue one. So what the result that you got looks something like this, purple. Okay, and then you take scale normalize. You take a scale normalize, which means that you are multiplying this this second derivative of Gaussian with sigma square, you multiply with that, all right? You multiply with that. You just amplified it, all right? So this is the result that you got, the pink one, all right? So then what you're gonna do, you're going to keep increasing the value of sigma. You're going to keep increasing the value of sigma. So to some point, if you start increasing the sigma to some point, this point, sigma is equal to 6.5. So we can detect the peak of this normalized response. We can detect the peak of that, but we cannot detect the peak of the other blob, right? So we can say that using a Gaussian kernels with this sigma is equal to 6.5, with this value, we can detect the blob A. So if we start increasing the value of sigma like that, so as you can see, as the sigma increase, the Gaussian kernel getting wider and wider, the peak getting dropped, right? So then if we increase to some point over here, the blob B will get detected because the peak over here will be the highest of among the three. And then we keep increasing again. Something like that. Blob C will be detected because this point is the peak among all the three. As you can see, as we increase the value of sigma, the peak of each blob over here of the scale normalized response start to decrease, of A and B start to decrease, but the peak of this blob C increase, so that we take a maximum among the three, so that we can say that this is a sigma value that we can use to detect a blob C. Right? So what does it mean here? What does it mean? So we can use a sigma. So the sigma here we call a characteristic of scale. All right. So as we change the sigma values, we can detect a different size of the blobs. All right. So we call a local extrema in X and sigma space. So to represent the blob with different size. All right. So to detect a blob with different size, what you're going to do is you just change the values of sigma. All right. To give you a more concrete example, let me look at going to this one first. For example, right? For example, let me give you a concrete example. For example, here we have the image. So this is our original image. Okay, this is our original image. And then after so we want to find the feature point, right? We want to find the feature point in this image. So what we are going to do is we are going to first apply Gaussian filters with different sigma. All right, so this is probably sigma 0, sigma 1, sigma 2, and sigma 3. So we increase the size of the sigma. So when you increase the size of the sigma, which means that when you increase it and then convolve these filters with the image will get blurry and blurry, right? Like last time you see when we apply the Gaussian with different sigma value, it's gonna get the image will get blurry and blurry. So this is how you apply different sigma value. All right. So you apply with different sigma value, right? And then what you're going to do next. So this one we consider let's consider this point, right? Let's consider this point. And then what we're going to do is for the same point, we want to find at which sigma that is this point has the highest value among every sigma that we are going to use. So here we have 4 sigma value, and then we apply this one so that we can say that at sigma 1, we got the peak of that one. So we can say that at this point, we are detecting at this pixel in this image, at this pixel location, red one here, that is the features or the blob that we are detecting. All right, so we want to detect a features point for now. We want to find a feature point or the blob that has a very unique features. All right, to find that, so the blob might have different size. So we want to find whether which size of the blob that represents a unique features at that particular pixel. All right, so if we're looking at this pixel across 4 different value of sigma, so we can say that at these locations of the pixel with this sigma, so that pixel at this sigma value, which means that we found the features by using a Gaussian with this sigma 1. We found that as a feature point by using that. But for the other sigma value, it might not look that obvious as a features. Okay. So that's what it means here. So what we are trying to do, we are trying to find a blob of features, right? We want to find a blob of features within the image with different size. All right, so the blob at this particular pixel, it might have different size for example, at this point. So we want to determine the size, how big the blob should be, all right? How large it should be, that blob size. So we are using this sigma to determine the size of the blob, because we know how to find the magnitude or the size of the blob, right? From previous class, we can calculate that. All right. I hope you remember from last class how to define the magnitudes of the features or using the Gaussian. All right. So so that's the purpose of what we are doing here, right? So we call the sigma star here as the characteristic scale, which means what is the size of the image, all right? What is the size of the blob, all right? So the characteristic scale is directly proportional to the size of the blob, all right? So that's the characteristic of that. And so like I said, we just take the argmax of that. So which means that among many of this one, we just select the argmax, which means you are just selecting the highest peak over here. So that's represent the features at that location of the pixel. All right. So if you're talking about the 2D blob detectors, so we are talking about 2D blob detector, we can use what we call a normalized Laplacians of Gaussians, right? So this is the Laplacians. I hope you remember from last class. This is the Laplacian equations. And then if we look at the kernels or the filters, this is how the Gaussian look like. This is the Laplacians of Gaussians. And if you take the normalized factor, which is sigma square, you multiply this sigma square with the Laplacian. So what we end up with is normalized Laplacians of Gaussian. It's just scaling versions of the Laplacians of Gaussian. All right. So so the locations of the blob is given by the local extrema by applying these filters, by applying these normalized Laplacians of Gaussians at many scale. So by saying scale is this sigma value. All right, so we keep changing the sigma value, and then we are applying this Laplacian normalized Laplacians of Gaussians filters to the image. So then wherever the local extrema is, that is where the locations of the blobs, right? So, so like I said, we can apply the sigma, right? We can apply the Laplacians of Gaussian here by changing the sigma value, right? So as we increase the sigma, the higher scale, the lower resolution, which means the image getting blurry and blurry. So that is the result of applying normalized Laplacians of Gaussians to the image. All right, so that's the first step of what we call scale space. Right, so we apply the normalized Laplacian of Gaussian here by changing the sigma value. So the question is what should be the scales of this? How many scale of that we need to do? So we can select the sigma by using these equations, right? So S probably maybe any constant multiplier that you can select. And then sigma probably any initial scale that you want to use, and then you just keep increasing the value of k from 0 to 3, so that you end up with the value of sigma that you can use. All right. So like I said, you just apply the Laplacians, normalized Laplacian of Gaussians, and then find the extrema or the peak across this characteristic scale, so that, which means that at these locations, that is the locations of the blobs, right? So for example here, if we look at these pixel locations, and then we at these locations we look at different value of sigma, so we can see that there is no obvious extrema, so there is no strong extrema here, which means that probably at this pixel location there is no good blob or no blob at all. All right, so so yeah, it is the same. You just apply that, take the argmax out of that, so you're gonna get the locations of the blob as well as the size of the blob. Okay. So for the SIP detectors, it used many tricks, a few tricks to make it both reliable and efficient. All right. So one trick is that we they use what it's called difference of the Gaussians. All right. So what we are doing here, we want to simplify the operations of normalized Laplacian of Gaussians. Right. We want to simplify these versions of that. So what we are doing here, we can say that if we are taking difference of the Gaussian, we can approximate the operations of normalized Laplacians of Gaussians. All right, because the operations of the normalized Laplacian Gaussians of Gaussian, probably it requires a lot of computational resources. So we want to simplify that operation. So we say that we can approximate this by using the difference of Gaussian, which means that you just apply a Gaussians, and then you apply the Gaussians with different sigma. You just subtract the two from each other's, so then you can come up with normalized Laplacians of Gaussian versions of that. So let's look at what I mean. So how exactly the SIP detector can find the interest point. Okay, so here's the image. All right, this is your image, and then with this image, you apply a Gaussian filters with different scale, with different value of sigma, right? So let's say that you apply 5 different value of sigma to this single image. Right, so you apply this 5 value of sigma, so this is what you end up with. All right, so next we are going to find the difference of the Gaussian, which means that we want to so our objective is to find the blob light, right? So we want to find the blob. So in order to find the blob, we know that we need to apply a normalized Laplacian of Gaussians. But we know that we can approximate the normalized Laplacian of Gaussian by using difference of Gaussian. So what we are doing is that first, find the Gaussian first. Find the Gaussians, apply Gaussians with different scale, all right? And then we subtract them. We subtract them from each others. For example, here, they are here. Let me see. Right. So for example, here, we have the image with sigma 1 and then sigma 2, sigma 3, right? So you apply the Gaussian with different sigma. So we have 5 value we apply. And then we subtract sigma, this result, sigma 1 and sigma 2. So this is what we end up with, right? We end up with, so what we are subtracting is just pixel by pixel value, okay? You're just subtracting for that. So you're gonna end up with another image, another versions of image. All right, you're subtracting, you keep doing this for every pair of the image. So that's what we are doing here. We are doing difference of Gaussian that is approximately equal to normalized Laplacians of Gaussians. All right, so because our purpose is, just keep in mind that the objective is to find the blob, right? So next, after we get the this difference of Gaussians, so then we know that after we take, we find the normalized Laplacian of Gaussian, and then after that, we need to find the extrema, all right, the peak among all of this. We need to find a peak among all of this, all right? So what we have here is we have a stack of images, right? We have a stack of images resulted from different value of sigma. So we apply filters, just like a grid, right? We just write a grid. So what does this grid do? It is nothing but the area that we want to look at. For example, we want to find. So let's say that we are using this 3 by 3 grid, all right, 3 by 3 by 3, which means we have a cube, something like this. We have a cube, right? We have a cube, which is 3 pixel, and then this side also 3 pixel, and then this one also 3 pixel, right? So you have a cube 3 by 3, and then you sliding this cube over this stack of the image, all right? So you have a stack of the image, something like this, all right? This is your stack of image. So you have each image, right? This is your each image. Each piece of paper is your one image. So you have a stack of them. You have a stack of them, and then you apply a 3 by 3 grid. Let's say this is your 3 by 3. This is your 3 by 3. So you're just sliding it over a stack of image. You're just sliding it over a stack of image. All right, left to right, top to bottom. All right. So you're sliding that. What you want to do is that, for example, this 3, right? This 3, you're first sliding this. So this is the area that you are looking at for this 3 stack of the image. So you are looking at the locations or the pixel location that has the extrema value from this one. All right. So you found this. Let's say that, for example, at this one, you find that this is the locations of the extrema value of that. So we mark that as interest point candidates. All right. So we keep doing this for all the stack of the image over here, and then we are going to end up with another set of image with the interest point candidate. That is, we can locate them for now. Okay.
Question.
Yes.
This cube 3 by 3, is there any specific value?
No, there is no value. It just define the bounding box of the location that we want to look at.
Okay.
Yeah.
So just they scan and capture that one.
Yeah. So it just the area, it just define the boundary of the area that you want to look at. And then within that area, you find the maximum value.
Okay.
All right. Within the cube, you find the maximum value. Okay.
Yeah, thank you.
So so then you can identify this interest point candidate by using that. All right. So next. So next, we are going to, so at this point, we probably might have some like a very weak extrema, which means the peak that's not quite unique. Right? That's peak that's not quite unique. So we probably further removing a weak candidate by just using some threshold, right? We using some threshold, and then we can filter out some of the weak candidate so that we end up with what we call a safe interest point over here. All right. So the centers of each circle, for example, we might find some peak locations across different scale of the sigma here. So the centers of each circle correspond to the locations of that features, right? And the radius of the circle is proportional to the size of the magnitude, or we call the magnitudes of the blob, right? So how do we find the magnitude of the blob? Let me see. Sorry. So the magnitude of the blob can be determined by the sigma value that we applied to, right? So let's say this is the sigma 0, right? Sigma 0, which means the smallest sigma. So we can calculate the magnitude of this one, or the size of this one, by using that sigma. All right. So that's how you detect a safe interest point. So here's the example of the SIF result. So after you perform the SIF, this is what you got. Okay, you got many interest point with different size. All right, with different size of the circle. So this circle is the size of the blob itself. Right. And so this is also like the SIF detector that can identify the blob or the interest point with different size. So that's the result of the SIF detector. All right. So the SIF detectors, which means that by the name imply, it has to be a scale invariance. All right. So it doesn't matters how the size of the blob is different. So we can certainly normalize the size of the blob so that the scale it's invariant. All right, it's invariant to the scale of the objects that we are interested in. Right. All right. So this is how we detect the interest point. All right. Any questions? So first, so in order to perform feature matchings, first we need to detect it. All right, we need to detect the locations, the magnitude, and the orientations. So these are three information that we need: where it is, that is the locations; how big it is, that is the magnitude or the size; and then what is the orientations of that. Right. So these are the information that we need. So we have found it, and then we have found the size of it by using SIF detectors. All right. So now next we need to find the orientations of each blobs or each interest point that we have already found. So how do we find the principal orientations of each blob? So this is the blob, right? So each circle here is the blob. So we want to find the orientations of each blob, all right? Because, for example, if you have this image and then you have another image of this one, it probably in different orientations, all right? So you want to find the interest point orientations within the two image, so that when you match the two image, you know how to rotate them so that they align together. All right, so you see that later, but just that the idea. So what we are doing here, we want to find the orientations, or what we call a principal orientation of each blob, of each circle. All right, so we know that we can find the image gradients directions by using these equations. Theta is equal to arctan of the partial derivative of I with respect to y, and the partial of derivative of image different to x, which means the directions in y the gradients directions in along the y-axis, and the gradient directions along the x-axis. So we can find the orientation by using this. So what we are doing, for example, this is the size. Oops. For example, this is the size of the blob that we found. So what we are going to do is that we are going to have some table, some grid. We map the grid onto this circle, and then at each pixel, we know the gradients of that pixel. We know the image gradient directions of each pixel. How do we know? Last class, we already discussed about applying the gradients. So how do we find the gradients of each pixel within the image? So we know that already, how to calculate it, right? So so next, how do we find that the principal orientation is that we just perform a histogram of that. So which means that which means that we are counting number of the gradient directions under this grid of this blob. We are just histogram, putting them in the bin, counting the number. For example, these gradient directions, for example, have 5 of them within this circle, and then this probably 30 degrees probably have like 6 of them. So we are just performing histogram of this, and then we look at the one that has a maximum value. All right, the one that has a maximum value. So that's what we call a principal orientations. It will represent the orientations of this blob, entire pixel. All right. So, but what's the use of this one? All right. What's the use of this one? So the use of the principal orientations under rotation. For example, you have the image of these two, right? You have the image of these two, and then you perform a shift detector. You found some features, right? You find interest point, and then you want to match these two, right? You want to match these two. The first thing you have to do is that you need to rotate them so that they have the same orientation first before you match them, right? So in order to rotate them to the same orientation, so that's where the principal orientation comes in. So you are going to find the principal orientation of every blob here. For example, the principal orientations of this blob, the big circle, the orange circle, right? So after you find that one, you can use this principal orientation to rotate the image, right? You can use the principal orientation to rotate the image like this, so that a book in this image align with the book in this image, so they have the same orientation. So you can use the principal orientations to undo the rotations. All right. So that's what the principal orientation. So at this point, we have found the locations of the interesting point or the blob. We have found the magnitude of each blob, the size of the blob. we have found the orientations of each blob, which is a principal orientations, right? And next, in order for us to be able to match between objects in one image to another image, we need to find what we call the representations or the descriptor or the signatures. So these keywords are using interchangeably. So in SIF algorithms, how do they represent each blob, right? What is how can we create a signature of each blob? So here's how. So we are doing quite similar to what we did when we find the principal orientation, which means that we are just looking at one blob, and then we take a grid. We just put a grid over that blob, and then the same thing. We are counting. We are doing a histogram of the gradient directions over this blob. All right, but the difference is that we look at this area, the first quarters of this grid first, and then we perform a histogram over this area, the first quarter of that, right? So we get this one, right? So we are performing the histogram over this area, and then we got this, right? And then next, we're performing the histogram over this area. We got this, and then we keep doing that quarter, first quarter, and the fourth quarter. So we concatenate them together. We concatenate them together. All right. So this histogram represent what we call a descriptors of this particular blob. All right. So that's the signature of the blob. So that's how we create a signature of the blob, right? So we got the histograms of the image gradient directions that represents the signature of that particular blob. All right. So we keep doing this for all the blob. So by doing this, the normalized histogram here, it is invariance to rotation, scale, and brightness. So it doesn't matter because we are considering only the image gradient, right? So that so now you have found descriptors, which means that for each and every blob within the image, so you have two images, right? So you found the blob, and then you found the descriptor within this image as well as this image, right? So so that you want to find the corresponding point between the two images of the same objects, right? So you need to compare whether one point in the image, in the left image, equal to which point in the right image. All right, so you want to find the pair of each feature point. So what we can do is that the first method, probably we can calculate the L2 distance. All right, so the descriptor is just nothing but a histogram, right? It's just a histogram of gradient directions. It's just a number, right? It's just a number. So in order to compare the similarity of the two descriptors, probably you just calculate the L2 distance. This is the equations of the L2 distance. So you have a histogram of one blob in the image, and then you have another histogram of the blob in another image. So you calculate the distance, L2 distance between them. If they are perfectly matched, so the L2 distance is equal to 0, right? Because they are perfectly matched. So every number in the histogram is the same. You subtract them, you calculate this L2 distance. If it perfect match, it has to be 0. But if they are very similar, it probably close to 0, probably 0.00 something. So the perfect match or the ideal value after calculating the L2 distance, it has to be 0. So that's the ideal conditions. Okay, so that's the first method that you can use. Or the second method, you can use a normalized correlation, right? So this is the equations of normalized correlations. So if you are using this method, the features that are perfectly matched between the two images, this distance has to be close to 1. The perfect match has to be 1. All right, they're just opposite. L2 distance, perfect match has to be 0. For the normalized correlation, perfect match, this value has to be 1. The distance between the histogram has to be 1. All right. Or you can use the intersections. All right. This is the third method, how you compare the descriptor between the two images. So using the intersections, the larger the distance matrix, the better match, which means they are very similar. That's why they are overlapping. So if the value of the intersections getting higher, which means they are better match. All right, so we find the intersections. So this is another method that you can use to compare the SIF descriptor. All right. So this is the result. If you're using the SIF detectors and SIF descriptor or SIF algorithm to find to perform the objects detections or objects comparisons between the two images. For example, here's the two image, right? Here's the two image. This is image 1. This is image 2. All right. So you want to find this image within the image, within this image 2, within the image 1. You want to find some objects, right? So you just need to do a SIF detector in both image. So you get a key point or feature point from the two image. And then after that, you perform the SIF to find the signature of each one within each image. And then you compare the SIF detectors or the features between the two. You compare them and then you find the match or the corresponding key point between the two. All right, by using the L2 distance, L3 distance, L2 distance, intersections, normalized correlation. So for example, you want to know the corresponding point of this red point in image 1. You want to know where is the corresponding point in image 2. So you just compare this signature of this point with every signature in this image, so that probably you find the pair over here, and then so that's where you find the corresponding point. All right. Or like I mentioned, the SIF, it has a scale invariance, which means it does not matter whether the object has a different size, or it also can handle the object with different orientations. It can find the matchings between the two as well. All right. Or for example, you have a cluster, like a pile of books, and then you want to find some like a particular books within this pile of the books. So you can use a SIF detector to detect, even though the book is partially visible to the cameras, but we still be able to identify that particular books or particular objects within the image using this SIF algorithm. Right. So so far, before I move further, any questions so far? How SIF works? How can we detect the SIF features like the size, the locations, orientations, and then how we represent the SIF features, descriptors, and then how we compare them. So this is the 5 step that we discussed earlier. All right, any questions?
I think I got one. For
Mm-hmm.
the comparison,
Okay.
the things we have let's say one block, we have then you have four signatures with the four histogram in one block, and we put it in all that one in an arrays, right? Like this.
Mm-hmm. Yeah, it's just 1D array, one-dimensional array. It's just a
One
vector. That's what we call a vector.
is a vector, but the value inside is the pixel with I mean the count with based on the rotation, the direction, and the
Mm-hmm.
count of that direction, right?
Yeah, yeah. So
That's
let's say that under this blob, it
Mhm.
has grid. Let's say that 7 by 7 grid. So
Yes.
we have a total of 49 value, right? 49
Yeah.
directions here. So we
Mm.
just bin this 49 and then count it in each quarter of that. So we count it and then we put that value into the histogram. So then we can concatenate them. So we're gonna get a vector.
Yeah.
So at each elements of the vector represent the numbers of gradient directions within that particular quarters. Or if you look at it as a whole, the elements of each elements of the vectors represent the number of gradient directions under that blob. Yeah. Yeah.
Yeah, clear.
Mhm. Any others questions? All right. So what are the example or the applications of SIF that we can use? So of course the first one would be the panorama stitchings using SIF. So we are going to have a lab. So Yi will tell us how to do this today. Okay, so let's say that we have these two image. We want us to stitch them together, right? So which means that between these two, there's the overlapping area, so that we expect that between these two image that they have the overlapping area. So there must be some interest point that appear in both images. So that we need to find the features where they are, and then what are the signature of those, and then we just find the corresponding point between the two, and then we can calculate the transformations between these two images so that we can use that transformation to merge them or to stitch them together. Right, so we find the interest point, and we find the corresponding point between the two. All right, so and then we can warp them and then combine them together to create a larger image. So this is how we use SIF to stitch the image. So that's what we call a panorama image. Okay, so that's the one applications of SIF detector, right? So next, so like I said, we need to find a corresponding point from one image to another image. So this brings us to the last one. How can we match the features? Okay, so what we have discussing so far is we want to find a vector that represent each feature points, right? So we already found by using a histogram of the gradient directions. So that's the feature descriptors using SIF. So now we want to find a correspondent between descriptors in two views or two images, so that we can calculate the transformation between the two, so then we can merge them together or we can stitch them together. Right? So that's what we call a feature matching. Okay. So let's say that we have taken this two image, and then we found some features. All right. So the question is which point to match. All right. How can we find the corresponding point? So at this point, a features has a key point. All right, a key point is that it positions in one image, so to another image, and a descriptors, which is a vectors number that capture the characteristic. So at this point, for each and every point in here, that's what we call features. So it has a key point, which is the locations of each features over here. And then at each key point, it also has a descriptor, which is just a vectors of the number that capture the characteristic of each key point, or we call features. Okay. So the question is how can we match them across two view? So the first one would be, for example, given that these two image 1 and image 2, and then we so the question is how to find the best match between the key features. Let's say that we have many features in these two image, right? So the question is how can we find the best match of the features in image 1 to the features in image 2. All right. So the first thing is we need to define a distance functions, right? So distance function means we want to compare the two descriptors, whether they are looking the same or not. They are the same feature point or not, because each and every features or key point they have a descriptor, a signature, or a characteristic that we can say, right? So we want to find, we need to define a distance function so that we can use that function to compare between features. All right. And then we can test all the features in image 2 to find the one with minimum distance. So we have F1 over here, and then let's say that image 2, we have 10 feature points. So we are calculating the distance between feature F1 with every features in image 2, and then we pick the one with minimum distance as the base match. All right. So how to do that? So the simple approach is just we can just using the L2 distance. Where's my mouse? Okay. So the simple approach, give me a second. Right. So the simple approach would be calculating the L2, right? The L2 between the two features. So let's say that we have feature 1 in image 1 and feature 2 here. We just use L2, which is a sum of square distance between the two. All right. Remember that the feature F1 is just a vector number. Feature F2 is just a vector number. We just find the distance between these two vectors. All right. So the distance function that we can use, probably the simple one would be the L2 distance here. We calculate the distance between the two. All right. So sometimes, for example, in this two example image, it could be ambiguous, right? So as you can see, F1, it should be somewhere matching with this features, with this location, right? So this should be the correct one over here, right? But as you can see, probably many of these they are looking like the same. So it probably, when you calculating the distance between the F1 and every pair of this point, right? Every pair of this point, probably the pair that has a minimum distance would be this point F1 and this point F2 over here. So this is give you a wrong pair of features, right? So using L2, this might be give you a very ambiguous match between the features, right? Because it just consider the distance only. So if a vector look very similar in this F2, so then you compare features from image 1 to image 2, since they are very similar, so the distance probably have a very similar patterns, all right, similar value. So it will give you a very ambiguous matches in this case, right? So how can we solve such a problems? Right? How can we solve such a? Is there any better functions? So yeah, there's a better functions. So we can the better approach would be using what we call a ratio distance. All right, a ratio distance is that first, for example, you're calculating you have a ratio. This is a sum of distance, right? This is a sum of distance between f1 and f2. You divided that with the distance, absolute value of that distance between f1 and f2 prime. All right, so you calculate this ratio, right? f2 is the best sum of square distance match to f1 in image 1. So this is the best match, right? So this is the best match. And then f2 is the second best, is the second best match. All right, is the second best match. So you find this the ratio between these two distances. All right. So if the ratio is very large, which means the pair of this might not be a good one. All right. So you get the idea. So you have these two features in second image. So then you want to find a corresponding point of f1 in image 1 with the point in image 2. All right. So what you find is that you find that okay, there's 2 points. There's 2 points here in image 2 that are best match with the features in f1 over here. These 2 points. So this is the best match. This is the second best match. So you find the distance between this one and you find the distance between this one. You divide it, you make a ratio from there. If the ratio is very high, which means that this pair of f1 and f2 is not good. You won't make them a good match. All right. So that's what it means by using the ratio distance. So what we can do is that first we detect and describe the image, which means that we do the shift in one image and then we do a shift in another image. So we're gonna end up with the key point or the feature point with a descriptor. So that's what I call detect and describe. So you're gonna get a features f1, a set of features f1 of image 1 and a set of features f2 in image 2. So how do we match this one? So we are matching every features in f small one, every features in a set of this with every features in the image 2. All right, we are matching, we are searching, right? We are picking one features from image 1 and we are searching for the best match in image 2 for everyone. So we are searching that. So we calculating the distance between f1 for every features in f2 because you want to find the best match between f1 and f2, right? So you pick one point, one features in image 1, and then you scan with every features in image 2 to find the best match. All right, so after you scan, you're gonna get the best match and the second best match. So this distance would be probably the L2 distance. So you calculate the L2 distance for every pair of the image, the features in image 1 and in image 2. So then you pick the two best match. You pick the two best match. All right, so which is f2 and f1, that is best match with f1. And then you find the ratio between these two. You find the ratio using which is this one, right? You find the ratio. So if this ratio is less than some threshold, so you can set this threshold. If this ratio less than this threshold, you are saying that that is the point that is matching between the two image. You got that? So let me repeat this again to make it clear. So let's say that in image one, right? This is your key, your feature point, the red dot over here. This is the feature point, all right? And that image one, and then image two, you have this feature point. Let's say this is the feature point, all right? So what you are doing, what you are doing is that you are going to pick, for example, F1 over here, and then you are trying to find the distance. First, you're finding the distance between F1 with every feature point in the F2, right? You calculate the distance using L2 distance, all right? Using L2 distance, that's F1. You're finding the distance of F1 with every features in image 2. And then you sort them. Let's say that this is 1, 2, 3, 4, 5, 6, right? You sort them from max, from smallest to largest. Right? You sort them, right? So you pick the two base match, which means that by L2, which one you pick? The smallest number, right? The smallest value, which means that by calculating L2 distance, if the distance is very small, which means that they are very similar. So you pick the best two. For example, it probably the pair of this. So it probably the pair. So it probably at this point probably the pair of this F2 and the pair with this F2 prime are the two base match. All right, so now you get two distance, the purple one here. So you make a ratio from there. You make a ratio of this distance and this distance. All right, by calculating this using this formula, you get the ratio, right, from these two. And then you set some threshold. If this ratio is less than this threshold, which means that if this ratio of F1 and F2 divided by the distance between F1 and F2 prime is less than some threshold, you can say that the F1 and F2 are the pair corresponding point within these two images. All right, so that's what it means. That's how it works.
Okay, so you got two features, and then I mean two teacher F1 and F2 and F2 prime, and then you do again with the L2 between F1 and F2 and F1 and F2 prime with the ratio, right? And then you put a threshold T.
Yeah.
If lower than T, then it's matched to the first, right?
Yeah, it matched to the first. This ratio, it matched with this pair. This pair is matched.
Because you put the ratio, the first one is the first ratio.
Yeah.
I mean the derivative, what we call it?
Dominator.
The dominator, right? Because you can swap, right?
Yeah.
Either one. I don't know which one. I mean, because what I'm not clear, because you can put either one.
What do you mean? What do you mean by either one?
Okay, you put F2 prime first at the denominator and MF2 at the one.
So the one that we are putting here is the base match. Is the base match.
The first match.
The best match, not the first match. The best match, which means it has the smallest L2 value.
Oh, okay.
Yeah, so you probably calculate this. This is the smallest L2, right? And then this is the second smallest L2. So let's say that you have three pair. You have three pair.
Yep.
So this is probably 0.1. This is probably 0.1.5. This is
Okay.
0.2. So this is
Yes.
the best match.
Ah,
This is the second best match. This is the
yes.
third best match.
Yep.
All right. So the one that you put in here is the best match, which is this one, the smallest L2.
Mm,
And then the one that you put here is the second best match which is this one.
mm.
That's always be like that.
Okay, clear.
Okay.
Thank you.
So you keep doing this for every point in first image. So you keep doing the same procedures until every features has been calculated, right? So you're gonna get a pair of every features. So you loop in F, right? You keep doing that everything. So you're gonna add the match. So finally you're gonna get a set of matches point between the two image. Right. So that's what we call a corresponding point. Right. So something like this. So after we calculate the feature SIF detectors and the SIF descriptor between the two, and we found the corresponding point between the two. That's what we end up with. Right. So the thresholds, it depends on us. So if we change the threshold either up or down, so the number of corresponding point will decrease or increase. It depends. Right. It depends on the threshold that we are setting. Right. So that's the image stitching. I mean image matching. All right. So I think let's first take a 10 minutes break, and then we'll come back at the image stitchings. And then after that, we will have a lab. So I hope it will give you a better ideas of how it actually works in actions. All right, so let's come back at 3:36. All right.
Okay.
Another question.
Yes.
The threshold of ratio is a number, and how can we define this threshold of ratio?
So how can we define the threshold? It just we first just arbitrarily divide it. So the best practice we start with 0.7 is I remember correctly. So the ratio started with 0.7 first, and then we'll
Yes.
see how many matches that we get, so we can increase or decrease this value. So by best practice, we start with 0.7. I remember 0.7 or 0.5. I remember correctly. Yeah.
Yes. Thank you, Professor.
Yeah. Any other questions? Right. If not, I'll see you at 3:36. I mean 10:36. Great. Is everyone back? All right. I hope everyone is back. Okay. So if you guys back, just maybe probably left types 1. So then we know is everyone back. Okay. All right. So let me just start it. So what we have been discussing so far is so we first using SIFT to detect features, right? So we're using SIFT to detect the features, and then SIFT can also give us the descriptors of each features or the key point that has been detected. And then after that, we find the corresponding point between two images, right? After we after we detect them. So then, and then after that, what we are going to do next is that after we find the corresponding point, we are going to use those corresponding point to stitch the two image together, right? We are going to use, apart from detecting the image from the objects from one image in another image, we can also use these applications for stitching the image together as well. So now we are going to talk about that. So the image stitching is first, how can we align these images together so then we can stitch them together. So that's the question. For example, we have these three images taking from different viewpoint, right? So then first we want to align them so that we can stitch them together to create what we call a panorama, right? So that's the purpose. So first, we have to find the corresponding point using a feature detector like SIFT, right? So we find the corresponding point across these three images between the pair of images. So for example, image 1 and image 2, and then image 2 and image 3. So we find this corresponding point. And then next, we have to find the geometric relationship between the image, right? For example, we are going to take image 2 as a reference image so that to align these three images, we have to find a geometric relationship between the image 1 and image 2, and then image 2 with image 3. All right. And then after we find the geometric relationship, that is how to transform the image, like image 1 to image 2 frames, and then image 3 to image 2 frames. So then we can warp image so that the corresponding point are aligned together. All right, so that's are the main three steps to create or to stitch the image together or to create a panorama. All right, so there's the another problems that after we align the image together, so we might probably sometimes or most of the time we might probably have a problem of seams. So that is as you can see here, we have a vertical lines that has a different brightness from the coming. After we align the image, we probably have the brightness as a seams over here. All right, so we can use a technique to blend the image to remove the hard seam so that the image looks very smooth. All right. So like I mentioned, in to align the image, we need to find the geometric relationship, right? And that that geometric relationship, we can achieve that by using geometric transformations that we have discussed in last week. So we have perspective projective transformations, affine transformations. So all these transformations we can use to we can use to find the geometric relationship. But for image stitchings, the geometric transformation that we are going to focus, and most of the time in computer visions, that the transformation that we are mostly focused is called projective, or sometimes it's called perspective transform, or another name you would probably hear is called homography. All right. So homography is the geometric relationship between images. All right. So these are one types of the transformations. So let's talk about how can we compute homography. Right. So from now on, I will use the word homography instead of perspective transform or projective transformations. All right. So how can we compute the homography? How can we find the homography, which is geometric relations between images? Which means that how can we align the image? What is the transformation that we use to align the image together? What are the metrics that we use to multiply one image so that it transforms to another image coordinates, and then the corresponding point align together. All right. So let's start with we have already discussed about the pinhole camera, right? So we have cameras, and this is a pinhole, and this is a image plane 1, right? So we are taking the image at this viewpoint. So this is our world, for example, any scene. So we are taking the image at this point, and then we rotate the image, and then we are taking another image, which is the image pi 2. And then we take another image, which is the image pi 3. So now we want to find the relationship between these 3 images. All right, we want to combine them together. We want to stitch them together. So how can we compute the transformations or the homographies between the 3? So there's a theory that if the image share the central projection in the sense is the pinhole, if they share the same central projections, so we can say that the image can be mapped to a single plane by using homography between the image. So what do we mean is that, for example, this is our image plane P. All right, this is the image plane P. So we mapped, so we can project by using the same central point pinhole here over here. We can find a homography that we can project the image from pi 1 to the image plane pi p over here by using a homography HP1. All right, which means that we are mapping from image 1 to the image plane P. We are mapping the image from here to here. Similarly, we can do that by mapping the image 2 to the image plane pi p over here by using a homography that is mapping from image plane 2 to 1 first. So you are mapping here the image 2 to the coordinates of image 1 first, and then from that you can map from image coordinate 1 to the image plane pi p over here. So you have a 2 homography over here. From going from image coordinate 2 to image coordinate on image plane P over here. Similarly, for the image 3, you are going from 3 to 1 and then 1 to P. All right, so you emit 3 to 1 first and then 1 to P. All right, so that's how you can map or you can project the image onto the image plane pi p. All right, so for example here, how can we compute that? So we given a set of matched features, right? We already know how we can find a set of matching features between two images. So to find homography that base agrees within the match, which means that if we have this set of matches features, right? So to find the homography, we want to find a homography that base agree by all these matches point, right? So how can we do that? So I'll mostly skip mathematics here, but I will tell you just give you the idea of how it works. So what we want to find here is that we already know this projective or perspective transformations, right? We already know this that it has the 8 degree of freedom, right? From previous class that we learned about projective transformations. This is one, right? It has 9 parameters. It has 9 unknown parameters, but it had 8 degree of freedoms. I hope you remember the 8 degree of freedoms, right? So what we need to do is that, what we need is this transformation matrix, that can transforms or maps any point in source image to the destination image, which means that if we map this point, red point, using this matrix, we are going to end up at these locations, in the destination image. Okay, so in order to come up with this matrix, we need a minimum of 4 matching points. All right, we need a minimum of 4 matching points so that we can calculate what is the homography over here. So to calculate a transformation matrix with 8 degree of freedom, you need at least 4 matching pairs, 4 pairs of matching points to calculate that one. Okay. So I just skip all this mathematics. So basically, we want to find this matrix by using some of this what we call a constraint least square. So you have this kind of unknown matrix A, which is a pair of point in source and destinations, right? You have a source and destination. That is, that's what we call known matrix, because locations, features or locations of each pair of matching point in the image, right? That is, allocations of this point in this image, and also allocations of this point in this image. So every locations of every point in this image. Everything in here as well. So that's what we call the term A. This is what we know. But what we don't know is the H over here, which is unknown, which is the homographies or perspective transform. So this is what we want to find, all right? So this is what we want to come up with. So by solving the problems of this mathematics, AH is equal to 0, and then the magnitude of H is equal to 1. So this is what we call a constraint least square problem. So we are solving this sort of least square problems. So, and then we define some sort of loss functions, something like that. So we're gonna end up with some sort of the H, which is this. What happened with my keyboard? Give me a second. My keyboard is a battery, I think. So what we basically got after this one, so we're gonna got this matrix H, which is the homography. So after we calculating this all mathematics, right? So what we end up with is this homography by using this one, all right? So at this point, you find the key point within the 2 image, the matching between the 2. And then you can calculate the homographies or the transformation between the 2 images. But what if there might be many good matches, right? But there are still some few few of the unmatchings, or what we call the outliers, right? So there might be some of the pairs of match point that are wrongly matched during our matching process. All right. For example, this point might be wrongly matched because they're at this point. They're not looking the same. They shouldn't be the match, a pair of match point, but they are. All right. So this is what we call the outlier. So if we take everything in here, if we take everything, including the outlier, and then we use every point in these two images to calculate the transformation. So that we might end up with not a robust or not quite correct transformation between the two. So how can we handle such a situations? So that's what brings us to what we call the algorithm of RANSAC, random sample consensus, which means that we want to find the transformations that only perfectly match or can be computed by only the point that is perfectly matched between the two images. All right. So what is the idea of RANSAC? So RANSAC is how it works. Let's look at the example first. All right. So for example, the blue dot here is your feature point. Your feature point into images that is your matches, right? And then you want to find some equations. You want to find some equations, or what we call models, that represent the whole data set, the whole sample. You want to find some equation that represent the whole sample. All right. So here's the example of how RANSAC works in finding the linear models, right? This is finding the linear models. So this blue point is your sample. So what you first is you pick any set of point, and then you trying to come up with the equations of this green line, right? This is your linear models. And then you fit your linear model with the red line first. That's your sample size, all right? You fit that first with the sample size. And then after that, you consider every point in here and see whether they are fitted with the line or not. The majority of this blue point of this sample fit with that models or not. Right? So let me recap this again. The first thing you have to do, you sample some certain number of points from the whole data set. All right, from the whole data set. So the sample in this example is a red dot. Okay, you sample that, and then you fit, or you find the equations. You find the equations that is best represent this set, right? Which is this line, the green line. All right, and then after that, you get this equation. You get this one line of equations. Let me see. So let's say that this is your first initial, right? And then this is your first sample point over here, something like that. So you are using this many point to calculate or to come up with the equations of this line. For example, you get x mx plus b, right? Mx plus b, mx plus b. So this is the equations of this line. For example, m probably 10, x probably 20, something like that. So you get these equations of the line. All right. So then after that, you calculate the distance between each and every point in the data set to this equation, to this line. All right, to this line. You calculate the distance, and then you sum them all up, and then you see whether the distance of everything, if this line represent the whole data set, which means that most of the dot sample here perfectly align with these equations. So the distance will close to zeros. All right, the distance will close to zero. So if the distance is still quite large, so you resample, which means that you might randomly pick another set of sample, and then you fit another line, and then you keep doing this repeatedly. Finally, you will come up with the equations that has a minimum. They had a minimum loss function, which is the distance that is close to zero, the best match, after you recalculate with everything in your sample set. All right. So that's the RANSAC, how it works. So that is the algorithm, right? So first you sample, you randomly choose some S samples, some, for example, 10, 20 points, right? And then you fit the models, So for homography, we need at least 4 points, right? We need at least 4 points to fit some models. And then we compute, which means that we fit the models to the point that we are chosen, the red dot. And then we score it, which means that we count the numbers of points in the entire features. Let's say that we have 100 matches point, and then we sample only 4 points, and then we compute the model that fit within the 4 point, and then we get that models. We fit that model with the entire data set or sample or features. We fit everything. And then if we count the number of features that perfectly match with these models. All right. So we repeat this process until we reach some certain threshold. So let me give another example. Let's say that we have 2 images, right? We have 2 images. We have this point as a feature point, right? We have this point as a feature point. So our features. So one feature here, we can view it as one-dimensional vector, right? One-dimensional vectors. So what we are going to do is that we are mapping this. So let's say that one-dimensional vector, this vector is a vector has 128 dimensions. Okay, which means that we have an array of 128 numbers. All right, so let's say that this is your image. Each dot over here is your feature point. So for each feature point, it has a signature that is your key point. Okay, so your key point can be represented as a vector of 128 dimensions. So you have an array of 128 numbers. So you project this onto a 128 dimensional space. So you project this dot, probably end up here, and then you project everything. Probably you have something like this. Okay, you project the features onto a feature space. So that's what so-called. So you project this already. So you want to find a model that is perfectly represent this set of data. Okay. So what you have to do is then you need to sample. For example, let's say that I sample this point, and then this point, and then I find some sort of models that it fitted between these 3. For example, I might get with this kind of parabola equations. All right. And then, so this is the model I first got. And then after that, I use this model to count the number of everything in here. How many points of these features that agree with this model, which means that so this entire model, this entire data set can be represented within these equations. That's what we are going to do. So if we count the numbers, and for example, here is our equation 1 or model 1, right? So we have let's say that we have this number of feature points, 100 feature points. And then for model 1, after we fit that, we have only 10 features that perfectly match with this one. So we keep it as it is. And then we resample again, we resample another 4 points. Let's say that we resample this 4 points. And then we compute the equation for this 4 point again, fit that. For example, we end up with model like this. All right, so this is the equations of this model. And then after that, we count the number of points that agree with this, which means it fit with all the points. Let's say that this is M2, right? This is M2. M2, there are out of 100, there are probably 20 points that are agree with this. So we keep repeating this. We keep repeating this sample. Let's say that we repeat this 10 times. All right, from M1 to M10. All right, so that the thing that we are going to choose is the M model here that has the largest number. Let's say that, for example, our M5 has 99 point from here that agree with that particular models. So we choose this model as our transformations or homography. So we choose this as a homography, which means that we can use the equations. We can use this equation to transform between these two features from the two image. All right, so that's the key idea.
So that means finally you want to find the best fitting mathematical model, like a line fitting that go through many inlier point, right?
Yeah, right. Yeah.
And it's in 2D, and in 3D you want to find a plane that go through many inlier point.
Yeah, right. Yeah, that exactly like that. Yeah. So you want to find a models, a line, a plane that go through the inlier that is represent that set of sample.
Okay.
Yeah. So yeah, that's exactly what it is. All right. So the RANSAC will work perfectly fine if the number of outliers is less than 50%. All right, so it's still working perfectly. Right, so yeah, so the question is how big is S, right? How big it is, how many number of sample that we need. So the question, the answer is it depends on what transformation that you requires. For example, in our case, we want to find projective transformations or homography, which has a degree of freedom of 8. So the size of S, which means the number of sample, is equal to ceiling of degree of freedom divided by 2. So the projective transformations has 8 degree of freedom, so divided by 2 is 4, which means that for us to find a transformations with 8 degree of freedoms or homography, we need at least 4 point. All right, we need a little of 4 point to find that. Okay. And how many times we need to repeat this process? All right, how many times we need to repeat this process? So you can use these equations to find the n time, how many times you want to find the log. All right, so it depends on the proportions of outlier that you want. All right, or the outlier that you expect the model to handle. So you can use, so P is a probability of the right answer that we want. All right, probability of the right answer that we want. So we surely that we want very high, probably P is equal to 0.99, right? So because we want the probability of the right answer to be high, and then it depends on how many percent of the outlier ratio that your models can tolerate. All right, so you can pick from this. For example, if S is 4, the proportions of outlier would be probably, if 20%, so you probably can set E to 9, for example, something like that. Yeah. So this is how you calculate how many times this iteration is going to loop through, right? So what we have been discussing so far is, so we have calculate the feature point of each image, and then we found the matching or corresponding point between the two. And now we already find the transformations between the two images by using those matching points. All right. So now after we got these transformations, we can use transformation to warp the image together, all right, which means to align the image. So from to transform one image to another image coordinate, how can we do that? So that is what we call a forward warping, right? Forward warping. For example, here is your original image, right? So you want, so what we want to do here, we want to warp this image on the left to the image on the right. Right, we want to warp this image to be in the coordinate frames of the next image, of the second image. So for the forward warping, which means that we apply the transformation, which means the homography that we found, we apply this transformation to every pixel in our original image. And then we find the locations, right? We find the locations of that particular pixel in the new coordinates, in the new image coordinate, right? So for example, at this blue dot, if we apply the transformation of this pixel, we probably end up somewhere around here. And then red and then green, right? So we didn't get exact locations. So we didn't know in the new image coordinate, we didn't know whether this blue dot should go to this one, or this one. All right, so we didn't know that. So after applying transformation, it didn't give us what exactly this blue pixel going to lie in this new image coordinate. Because when we are transform the image, right? We want the image to have the same pixel value, right? We want the image to have the pixel value, just the perspective is changing, right? So we want this pixel, if we transform to this image coordinate, we still want it to have a color of dark blue, right? So that's what we want to do. But after applying these transformations, we didn't know whether this blue should go to this pixel location or the pixel location or this pixel location if we perform a forward warping, right? So if we perform this forward warping, it's probably end up that our result can have a hole, which means that there's some certain pixel location that cannot be filled. All right. So that we have something called the backward warping. All right. So instead of applying the transformation, so we take the inverse of that transformations. We take the inverse of that transformations. Right. We take the inverse of that transformations, and then we going backward from the destination. So we say that if we are going, if we want to fill the pixel value of its pixel locations in the destination image, what is the pixel value that is correct? What is the pixel in the original image that is corresponding to this pixel location in the destination image? So we apply the inverse or backward warping. So we apply this transformation. So then we probably end up with somewhere around these locations, right? With somewhere around this location. So the pixel value of this pixel location in the destination can be the averagings of these 4 pixels. Right? There are many techniques that we can use, either a nearest neighbors or the interpolations of this location, so that we can fill the pixel value of the destinations. All right, so we can use either nearest value, or we can use like the average between of these 4 pixels to represent this value pixel locations, or we can use the interpolations to estimate the brightness in G. All right, so that's the invert warping. So now we are ready to perform the image alignment, right? So we are taking the image 2 as the alignment, all right? And then what we are going to do next, so we are going to warp the image 1 to the image 2 image coordinate reference, right? So we are going to create first, this is the image 2 coordinates, right? This is the entire space over here is the image 2 coordinates. All right. First, we are mapping, we are warping these 4 corners of the image, applying the homography so that we know the boundary of this image, the locations of this image in a reference image coordinates. We first doing this one, so that we know that this is the boundary, right? We know that this is the boundary of this image being warped onto the reference image coordinate. This is the boundary, right? And then after that, we are performing the backward warping, right? From this pixel coordinates, we are performing backward warping, which is we want to look for the brightness or the pixel value of these locations from the original one. So be backward from that, and then fill in the brightness in this location. We keep doing this for every pixel, in red boundary, and then the blue boundary from the image 3. All right. So finally, after we perform backward from that backward warping, so that this is what we end up with. All right. So after we overlaid it, this is what we end up with. And then we can see that the problem of seams over here. So we can see that the difference in brightness, right? The difference in brightness. So this probably happened because of the moment that we take the image, probably that the sun goes by, the cloud goes by, something like that. So we get different brightness in each image. So when we stitch them together, they have some, this is what we call a hard seams, right? So now we need to blend it to create a better image, right? We need to remove these hard seams. So what we can do first, the most easier and straightforward is just taking average, right? It's just taking average of the nearest pixel. For example, we are saying that we want to average the pixel. So let's say that we take a windows of 3 by 3. We take a window of 3 by 3, okay? And then we are saying that at these pixel locations, we are going to average all the neighbors brightness, and then we put it into this pixel. So average everything, and then we're sliding these windows. We're sliding this window to average everything. All right, so then this is the result that we come up with. So as you can see, after averaging the brightness of every pixel, there's still a hard seam that is visible over here. Right, so the question is there a better solutions to handle this, to blend the image together? All right. So yeah, there's a solution. So let's say first look at these 2 images. So if we want to blend this 2 images with this sort of weighted functions, right? So for the first image, we are using these weighted functions. So for every image in this size, we multiply them with 1. For the image with this size, we multiply them with zeros for this image. And then this image, we are just doing the opposite. the pixel at this locations, multiply with 0, and then pixel with this location multiply with 1. So then we just combine them together, pixel by pixel. So this is what you end up with. It's just a hard seam. It's just that you cut it off and you stitch them together directly. All right, so this is not good, right? So, and another functions that you can use instead of just 0 and 1. So you can use likely slope over here, all right? Going from 1 to 0. So it's just weighted functions. So for every image, for every pixel somewhere around here, so you multiply them with 1, so which is the original pixel value. And then for every image, so every image somewhere around here, all right, you are starting multiply them with 1 and then keep decreasing until they are reaching 0 here. So the decreasing ratio, it depends on you. Probably you can go maybe like 0.1 step, right? From 1, 0.9, 0.8, something like that until we reach 0 here. So you multiply this value with each and every pixel in this locations. So you do the same but opposite from the other one, and then you just add them together. So this is what you end up with. All right. So quite better, right? So quite better. There's no hard seam over here, right? So quite good at blending using these functions, right? But we can do better than that. So here's another weighted functions, right? That we can use to fix the hard seams, right? So we can computing a weighting functions. So in this example, we can say that the weighted functions that we are going to use is the pixel at the middle, getting a very high weighted, which means that their brightness mostly are the same, right? So the white pixel has a value of 1, right? So this is what we call, we created a grayscale image. Grayscale means we are ranging from 0 to 259, all right? So 255. So the 255, this is white, right? This is completely white. This is completely black. The value in between is just scaling between white and black, right? So this weighted function is saying that this area get a high weighted, which is 255. And then as it goes out from the middles, we are decreasing the value, we are decreasing the weight. All right, so which means that it goes from 255 and then goes to like 200, 100 something until it reaches 0 at the border. And then this is the characteristic of this weighted function. You can use any weighted function you can come up with, but this is one function that we can use. Okay, the pixel that closer to the edges get a lower weighted. So that's what it does here. So we apply this weighted function to this image, and then this image, and then this image. All right, so that's how we get this result. So after applying that functions, so this is what we got as a result after we blended the image. Okay, so we are clearly not seeing the visible seam over here, the hard seam over here. All right. So for this image stitching, you can probably you can see in many applications, you can taking multiple images of the same scene from different part of the scenes, and then you align them together by using these techniques of image stitchings, find the blobs, find the matchings, find the blobs, and then calculating the features descriptors, and then find the matching pair between the image, and then compute for the homography so that you know the transformation between the two, and then you use that transformation to to align them together, and then you use the blending techniques to blend the image together so that you finally end up with a perfect blended image finally from multiple images into a single image. All right, so yeah, probably that's it for the image stitching. Any questions? All right. If no questions, we have 40 minutes left. So Yi, how many labs you have?
Today I guess we have three labs.
3 labs. So probably you can pick the one that you can finish in 40 minutes first, and then in the afternoon we can continue another 2 labs.
Okay, that's fine.
Okay. So now I will hand it over to Yi. So then she will walk you through the labs, discussing about the things that we have been discussing theoretically in the lectures, and then how can we implement it in like OpenCV. All right, over to you, Yi.
Okay, that's fine. Hello everyone, can you see my screen?
Okay.
Okay, so in this lab, this is the lab number 4. It will cover 3 sections. This on the section 3 sections already taught by Dr. Joseph. And what we need to do now is we have some hand-on experiment for 3 of this, including the feature matching, image stitching, and panorama. I think for the lab of 40 minutes, I think I will cover the feature matching. And I hope that in this lab, you can also open the collab link by yourself, and you can parallelly do with me in case that you have stuck or something or have any issue, you can ask me directly in the lab. And okay. Can you check whether you can accept this one and let me know? We can start with the feature matching. Okay, for one more, you also need to have the resource here. You also need to go to this one because this resource can, contains many image that is can be the resource for our notebooks. So you can check. I think I can give you some minutes to set up all of this, and we can start together and go through the first one. You can go to the tube first and check the lab number 4. Let me know if you done that.
Let me copy the files notebook first.
Okay. Yes, sure. You should copy in your drive first.
Feature detector. Okay. Resource. See.
It's okay. You can put on the chat if you already copy to your drive as well as to access the resource link in the Google Drive.
On the way.
Okay.
Okay.
Okay. Oh, okay. Let me start to show you this lab now. There are some keywords that are already clarified by the Joseph. I just recall a little bit. The key point like can be, like a pixel or like a small region of an image, like to stand out from other its surroundings and can be detected and redetected in other image. It can be like corners, junctions, or blobs. That can be the unique local structure. And in the features that is kind we detect that sometimes is like semi-key points, and we can detect the feature, which means that we detect the key points. So the interest points is kind of the another name of key points, and it can be interesting because it have like more informative, distinctive, and it works for tracking and matching. Corresponding is like about the matching the key point between two images, right? Okay. You should. Oh, okay. Let's run this one. We need to connect to our drive. It's good if you already save the resource or link, and you will use that to load the image later. Okay. We also need to set the current working directory, and this is the directory that I serve for the resource link. Whatever if in your case that you have that another link, you should replace this line. There's some library that we should use, NumPy, Pandas, CP2. Yes, Matplotlib to load the image. Okay, and about this function, okay, and let's take a look at this. Because in this lab, we need to match. We have many cases that we match two images. We want to show many images together. So that's why and if in that two images, they can have the different heights, right? So we need to standardize them to have the same height, and we show them horizontally. So that's why we need this function first, and after that we can show many images on the same line. Like we use the height, the minimum of the height of all of the image, and we try to resize other image to have the same height, and then we show we concat them horizontally. So that's why we use this function. Feature detector. Okay. We given that we have many feature detectors in computer vision, and we want to decide that's which one to use. We can start with the hot transformation. For that is for light detection. Okay, I can maybe that I need to explain this one a little bit. Okay, for normal because what we usually found in the image, like this is the point that we found, and what we want to try to find the line. Let's say we find this line, and normally the line can be represented as we usually see like and it's, let's see, right? So in this case, the other form to find a line, they call that the rho is cosine theta plus y sin theta. So what is the rho? They say the rho that is the shortest distance from this one to here. That is another color. This one is the rho, and the theta, this is from this line to the x-axis. So they use this because this version like can work for online, for on the lines like horizontal, vertical, and the rho is, as I say, that is the shortest distance from the origin. Let's say the green box is the image space, and this point is the origin, and this is the shortest distance from the origin to the line, and the rho here is the angle between the x-axis and the perpendicular line. This is this one, the orange. If you are more curious about how we can have this function, I can share you later. Let's start with this one first. So initially, once we have the point here, and what we need to do is we try to create a 2D array, and they call that is the accumulator. That's kind of be like, okay, that's we have the table like this, and what we need to do is the voting. This is the rho in this one, and this is the theta, and this is the rho, and we try the rho from minus 90 to 90, and every time when we find the rho, when we find we have the points, and we rotate the line from negative 90 to positive 90, and every time, and at that time we can calculate the rho, and we vote for every line like that. And in this case, and when we need the numbers of every point will increase, like will be implemented or voted up, right? So when and we will have the result, like if we do the result like 200, if the numbers of every group of rho and theta, we will choose that one as the line. We can see. Do you understand this one?
So the goal is you want to detect the line, right?
Yeah, we have many points in the image, and we try to find every line that go through the points, and Yeah, we choose the lines that have many voted by the rho and the theta.
Okay.
Let me run this part. This is to load the image of chessboard, and we find the edge of the image. And this line is based on the algorithm that I just mentioned. And we can flexible to change this number. This number is the number of votes in the algorithm I just said. If we increase the number of this one, which means that we're more conservative to detect the line go through the point. You can decrease if you want. Okay. This is the edge of the shape. And if we choose this position 500 by in 500 is the the zero stand for the black points, right? Let me show this one as the grayscale. Okay. This is the edge mark of the edge detection from the original image, and with the algorithm of how to detect the light go through the points, they define the line in the blue color. So we can also use the function that we define in the initially to show two images together. First one is the edge mark, and the second one is the line image. Let's try with another image here. Can you load the image in your Colab notebook?
Yeah.
Yes.
Okay, that's fine. If you have any issue, you can ask me. Okay, for this one, this is the land rock, right? We want to find the lines, and we want to find the edge first by Kenny, and after that we find the lines. In this case, we choose the 300, which means that the number of votes higher or equal than 300. Let's say if we choose 200, which means that we less conservative. The line file can be even more. You see, that's kind of very noisy, right? So, but what we need to do is we find something that's more straightforward, and that's why we need to more conservative to increase the number of votes here by 300. And the result you see, that's very right with the direction of the rock, right? Okay, let's move next to the probabilistic Hopf transform. So in the Hopf transform, we see that even for a line that have two arguments, and that can take a lot of computation. So in the probabilistic Hopf transform, they consider that is an optimization of the Hopf transform, because it just takes the random subset of the points with really sufficient for the line detection, and that's why they call that is the optimized. Okay, and that can be, we have to they just to decrease the result, and they can see the image between the Hopf transform and probabilistic Hopf transform. The difference in the code is only the p here when we want to do in the probabilistic Hopf transform. Okay, the same. So they can also see the line in the green line here. And okay, as I mentioned that for the probabilistic Hopf transform, they have more optimized like algorithm for the optimization problem, so it should be less computation time, right? So I think here what we need to do is we need to compare computation time between the Hot transform and probabilistic Hot transform. Okay, let me try. You can try with me together. You can using the algorithm here for the Hot transform line to detect the lines, and probabilistic here to detect the slide as well. And we can compare the time between two methods to check whether computational time between Hot transform and probabilistic transform is different between them. Okay.
So same image, right?
Yes, with the same image.
Okay.
This is HCM. So this is for Hot transform only. So I test like ST, and the other one is this one. Is this one, right? We should yield the same of threshold to check. Okay. The difference here is that we need to check the time between that. So the start time. Start time. Listing probabilistic Hot transform, and okay, we use the steps on the same here. And calculate the probabilistic Hot transform here. And now is that we compare the time. Okay. 10. And this one. This one. Right. Okay, it can pull it. All transform time is really bigger. No, it's yes, it's kind of bigger than higher the time higher than the probabilistic Hall transform, right? So it's proof that the optimization has been worked for probabilistic in terms of computational time. Okay, now we move to the Harris-Cortner detection. Okay, if you remember, this is the cost. This is the coursework. This is the course lab of last week, right? To detect the corner can be in the window or the corner of the room or something like by the intersection between the line that can be considered as the corner. And we have the image of the building here. We load that image and check that in the ray scale, and we check we see whether okay. This is the result, and they usually consider to use it between this number 0.04 to 0.06, as I remember, to see the corner. Let's try with another image. It's also the building. Again, that we use the function that we initially set up, initially defined to see between the image that we already detect the corner with the original image here. Have you run this one? Okay. Okay. We move on to the cytomassive corner detector. So actually, it also have some mathematics behind, but I don't go very detailed about that. But we can think of that in this way. This is the scoring function in Harris-Cortner detector, and lambda 1 and lambda 2. That's actually the agent values. And in the Harris-Cortner detector, if the lambda 1 is small, the lambda 2 is small as well, that they call that is the flat region, meaning that they have no intensity change. And in case that the lambda 1 is large, the number 2 is small, which means that they have changed in one direction, and that region can consider by the edge. And if they are too large, and that can consider that is the corner. So instead of that, the Shitomashi, they propose that the R just be the mean of the lambda 1 and lambda 2. And this cytomass is kind of more, when they do the experiment, they see that it's often more accurate because it directly to check both directions are strong. So let's check with this the image that we share. We say that okay, the detection here. We use the circle to see the corner of the image. Okay, now let's move on with the Kenny detection, Kenny edge detection. This is one of the experiment that Dr. just shared earlier. If you done your assignment, maybe that you can use this algorithm to detect the light, and this can be used that's apply the Kenny detection, edge detection. I heard that one student asked about the discrete vector. That's actually the one dimension vector with 1 to a values, because in every region they divide it into the 4 by 4 pixel. That is 4 by 4 blocks, and in every pixel that have 8 direction. You can consider like north, south, west, and other I don't know, but for the other 4 direction can be like north south, northwest, or like the west of the south. Only that we have 8 directions, so that's why we multiply them and we have 1 3 8 direction in one direction vector. We detect the key points by using shift, and we use this function. Let we load the image and transfer it into the grayscale image, and we use the shift to detect the key points. So the key points include two things. First is the points, and secondly, if you see very detail here, we can also see the direction of that. This actually represent for the descriptor vector.
Question. Do we have any parameter in shift detector? No, right?
Yes. It's already the algorithm already at here in the state, so we don't have any parameter here to choose.
Okay.
Yeah. So when we compute the image to detect the key points, so there are two things that they can generate for you. First is the key points, and the second one is the descriptor. So the length of key points, what does it mean? Which means that they how many key points that they found in the image, right? So here they found 861 key points in the image, which means that the number of circle here, that is the number of key points. Okay, and descriptor, which means that the vector, right? The vector that they found, and the number of descriptor are the same, right? But when we see here, let me show. That is the vector. That actually have the 861 descriptor, but every descriptor is represented by the 1 to 8 dimension vector. So it have 1 to 8 elements in 1D vector. So
this means this image they have 861 features or glob or something like that, right?
Yeah.
And they have the direction.
Yeah, it have 861 key points in the image. Yeah, and in every key point you can see here. Yeah, that's the key point, and this one is the orientation, or they can say that the direction is can consider like the vector.
So the
And
direction is 3. So the direction should be from 0 to 360.
three,
Right.
three,
Right. Yeah.
yes,
And then that's one for the vector. So they store 128 of them, right? Yeah, correct. Histogram. Okay. Okay. Histogram. Yeah.
yes. As you said, they consider the first key point. The first key point is they use 0 as the first key point, and to extract the points, this is the first point. That is the dimension. That is the information of the first point. This is the x. This is the y, right? And we also have the direction of every key point, and that is from, this is the angle from the y-axis to that direction, and here is nearly to 380, 360, yes. And this is response. we can find the key points and calculate the descriptor. Yes, I think the technique is quite simple as long as we know how to use with the right version. In case that if they ask you to find the key points or calculate the descriptor by shift, you just simply use this code, and it can help you to detect the key points. Feature from accelerated segment test, we can use this one to also detect and draw the key points as well. It's very busy, right? So many key points in here. Okay. This is the order techniques beside the shift. They call that the oriented fast and rotated brief. It can normally to also to detect the key points and the descriptor of every key point in the image. You can see here. They okay. They normally call that RGB. Okay, and now we can move to the feature matching. When they say matching, which means that you have not only one image, you can have two images to match them, right? And to match the two images, we need to detect the key point of two images, and we try to find the key points. For example, you have one key point in the first image. You want to find the other points of the second image that they can match with each other. And in the last that we just learned is that we find the key points that have the shortest distance between two vectors, right, from the two images. Yeah. That's why firstly we need to detect the key point of the first image, then the second image, and we try to find the match between them. Here, they also need to find all of the matches between the descriptor first and the descriptor 2. And let's say that let me say how many match that we have. We have 260 matches, but let's check the first one. So the distance here, what we need to find is that we need to to find the match, the good match, we need to detect the distance and find the short one, right? So they use this function. This function is just like to sort them by the distance. The reason why we do that because we want to find the good match, and the good match is that, which means that the short distance between the two vector, between the two descriptor.
Yes. Okay.
Okay. That is just for the visualization to see that how they can match the key point between two images. I guess that the one student asked Dr. Chuck said that how we can find a good distance, right? So this is he answer that in the good practice that we use this number as the good weight ratio to find the good matches. Okay, we can, yes, I can summarize this. We load the image. We consider to use the shift for the detection, the key point detection, key point descriptor, and then we match them together. After that, we try to find the good ones. The good one is considered is the short distance between two descriptor, right? And we create the list of the good ones, and we append that if the distance is smaller than this number, we consider that is the good one. And after that, we try to plot them in the image. Yeah. Okay. What do you think if I decrease this number?
Reduce.
Yes. The number of the matching is degree or not? Degree or increase?
Yeah, we will decrease the number.
Yeah.
It's more rigid, I think. More harsh.
Yeah, it's more
threshold.
conservative. Yes, it's more conservative to find a good match, right? So the most, we see the modular detector between them. I guess I think that's all for the morning. Let me consider continue for in the afternoon after the lunch. Is that okay?
Okay.
Yeah.
Yeah, sure. So in the afternoon we will first start with the rest of the lab by Yi, and then I'll continue with the camera calibration topics. So probably we couldn't finish that, and then we will continue tomorrow mornings with that and the lab as well. So let's see how far we can go. All right. So I'll see you at 1. So yeah, let's have some lunch.
Okay.
Okay.
Bye bye.
Okay. Bye bye. Thank you, Yi. Hi, good afternoon.
Good afternoon, Dr. Susan.
Okay. So, I'm not sure everyone is here, so maybe we can wait a couple more minutes
Yes.
and then we will start the rest of the lab. Yeah.
Hello, Anh Quang. How are you doing?
Yeah, good. Just finished exercise.
What is the temperature currently in Vietnam?
Yeah, right now around 34 degrees Celsius.
Oh, yeah, it's pretty hot, right?
Maybe this morning, this evening, it will rain. So,
Oh,
yeah.
maybe you should give me some hot because it's really cold now, under 10 degrees.
Eh? Melbourne?
Yes.
10 degrees. Yes. Very cold.
Yeah, it's because now is the winter.
Eh?
Yeah, the winters can be between like June, July, and August.
Normal, this is the summer, right? Ah,
Yeah.
different. So from August to December, what's in weather?
This is the spring.
Spring.
Yes.
January to March.
And from December to February is the summer. So that's the hottest time.
Interesting.
Yes. So which means that if I'm here and in the December I come to Vietnam, so I can observe winter 2 times a month, 2 times a year.
Interesting.
Okay.
So if I visit Melbourne and Sydney on the around August, then it means that's in the winter.
Yes. So yeah, it's really cold. So suggest that you should come in the spring, like after October.
After October.
Yes, and maybe the autumn. Yeah, the autumn can from March to June.
Oh, March.
Yeah.
It's better after October, right?
Yes.
Best. I see. Yeah, June, July, August, September, October.
Do you have any plan to come to Australia?
Yeah, I still have plan. One of the partner invite me and CEO to the, not sure in Melbourne or Sydney, to visit their customer. In any case, he's also working in the computer vision
Oh, that's
domain.
cool.
He's work for the university and also have a company, private company,
Oh.
doing the consulting in the AI, especially in the computer vision.
Mm.
And yeah, but I'm lazy now.
Yeah, if you come this time, like you can escape from summertime in Vietnam.
I see.
Mm.
Yeah, but I'm very lazy now.
Okay.
Needs to finish the domain project industry first, and then
Yeah. Okay.
the project industry and also continue with the legal document. The same with the last one I doing.
Oh, the last one you're doing is NAV, right? If I
Yes.
remember.
So just continue it.
Mm.
But its span is a little bit
Thank you.
different.
Okay, everyone, if you back, can you give me some signals?
Hello.
Hello. Mr. Khoa, Mr. Hoàng Anh, are you back? Okay, let me start the class now.
Already, before so the lab that we are studying, which lab we are going to do now?
I guess that is geometry, projective geometry.
Okay, so yeah. So before you go to that, I just want to share some thought on SIF, because I've heard some of the students asking Yi about this sort of the creating the SIF objects over here, whether can we set any parameters or not, like, because in our discussions, right, in theory, in our theory, we say that for the SIF we can set either the sigma value and also the threshold, right? We can set the threshold to like finding the extrema, something like that, right? So so to eliminate a weak extrema. So all these parameters. So the question is, can we set any parameters here to define or to set these parameters or not? So the answer is yes. So if you look at the definitions of this function SIF create, so in this documentation from OpenCV, okay. So if you look at the function definitions here, SIF create, okay. So you can see that there are two versions of SIF create over here, but essentially they are pretty much the same thing, but just give you the more flexibility. So to just give you a short idea of what we can pass these parameters to, is that we can pass 5 parameters to these functions, right? Which is the same as this function here. So basically we can pass the parameters to this function so that we can set, for example, the sigma value, the threshold, the number of features point that we want to keep, for example, right? So these are the parameters. For example, the n features here, it's defined the number of features that you want to keep. So by default, it's set to 0, which means we keep everything, all right? And the second parameter will be the number, the n octave layers. It's basically, its default value is 3. So what is the octave layers? So here's the meaning of octave layer. So in each octave, right? In each octave, you apply the Gaussian filter with different sigma to the image, one image size, right? Octave 1 would be probably the image size of 1000 by 1000, and then you apply a sigma, you get some set of difference of Gaussian, something like that, right? And then you resize the original image. So, and then you apply the Gaussian filter again. So this is what we call octave 2. and then you resize it again, and then you apply the Gaussian filter again. So this is octave 3. So it's the number of time that you is the number of time that you resize the image. So that's what we call octave. Okay. So that's the octave. And then the third parameter would be contrast threshold, which means that the threshold that we are going to eliminate the weak extrema here. All right. So here we can apply the threshold here. That's what contrast threshold. And the third parameter would be the edge threshold. So it's basically just another threshold that we can set, right? And also the sigma value, we can also define the sigma value, what sigma value that we want to apply, right? So the rule of thumb that we can use for a selection, a sigma value can be used with this one, okay? But the default value is starting with 1.6. So that's the meaning of how you can control the parameters of the SIF function itself. All right. So you can try this function with these different parameters to see whether it give you the quality of the detection you need or not. So you can play around with those parameters for SIF detectors. All right. So yeah, that is it for that is it that I just want to share on this setting. Yeah, back to you.
Yes, okay.
Mhm.
Okay. Let's back to this.
Maybe you can like make it full screen for the Windows. Yeah.
Okay.
Yeah, that's better. Thank you.
Okay. Let me connect again to the drive. Okay, we just come to yes, this part, right? So let me recap a little bit. We find the match between two images by using the key points and descriptor of the two images, right? So okay, let we check the number of the match. That is the matching points between the two images. And this one indicate that we have 604 matches, right? So the order of this one is really matter because the first they stay here. That is the descriptor number 1, which means that that's the reference descriptor. What mean I say reference? Okay, we can check how many descriptor that's the SIF already detected from the first image. We have this number, right? And we also have the number of the descriptor of the second image. And we see that's the different number, which means that for every key point in the first image, they are trying to find the matches of from the second image. And That's why the algorithm here, we choose the KNN to choose the first two of the matches for which that match the best for every key points in the first image. Okay, for example, like if we choose the one key point in the first image, and then the algorithm will try all of the matches from the second image, and they ranking which one is the best one, and they choose the first two of the key points from the second image that match in the first image, and at the end we can find the same number of matches with the same number of the key points in the first image. So 604. So let's see, from every matches we have two key points, right? So we compare the distance of the first one is the best match with the second match, and if that is different around 1.79 to 75, that is can be considered as a good point, and we need to, and then that we visualize in the image to see here. And this is the last one for the feature detector. That is, they call the fast library for approximate nearest neighbors. We also have to find the key points in the descriptor with the shift, and we try to the algorithm try to find all of the matches, and this also have the same, and this is the parameters for the right for drawing here. Okay, I think that's all. Do you have any question? I can move on to the projective geometry.
No question.
Okay. Oh, wrong. This lab is about the projective geometry and homography, how we can do the homography in experiment. Let me put the try first. We also need to use this function to visualize multiple images in the same line. We have three images to visualize here. That is for the same subject, but with the different scaling, with different rotation, different translation of three images, right? And we contact with them to show. This kind of one of the application that we want to transform a subject into the new space that from here to here, that sometimes that we can capture documents would not in the right rectangular, right? We want to transform it in this way, and that's what we use the projective geometry and homography.
Yeah, just to maybe add a little bit, if you remember last week that I showed you the application, the Microsoft Lens. So that's what we are going to do here. We're just going to replicate that functions. So the screenshot that I took is from Microsoft Lens. So which is it is transforming the image to this background into the perspective projection here so that we get the final result. So that's what we are trying to replicate the behavior from there. Yeah.
Yeah. Okay. So for the homomorphy transformation number, as we in the morning we say that the degree of freedom is 8, right? So we need at least 4 points for the transformation. So for example here we have the image, and what the four points that we need to find, that is the 4 corner. That means that these 4 corner, let me write here. That's this one, the first corner, second corner. This is the, yeah, we need to find 4 points here. And what we need to do is that this is also another, okay, let me go. And what we need to do is that we need to transform it into this way, right? It's also the first gram, second gram, third gram, and fourth gram. That's what we need to do. And what we need to do is that we find the transformation here. We have to find the transformation from the first image to the second image, and we need 4 points to do that. Okay, so we need to find 4 points here in the coordinates of this image, and we transform to here. Okay, let's look at this image. The first corner, this is the shots of the corner. So we have this image as the original image, and this point, if we can see here, this like around 30 and 40 something here, right? So we will use this array to indicate all of the shots of the corners. This is the first one. The second one here should be here, right? Is the we project here in like 700 something, and project here is like 100 something. So that is the second one. The third one should be here, and the fourth one is here. And the destination corner that we want is okay. Let me go again. So the new image that we want, that will be 640 by 480. So this one, the point is 0, 0, right? So, and this one, it should be like right? The third one here is like 0, and this one is, yes. This is necessary to find all of the points of the source image and the destination image that we define here. That is 2 arrays. And we need, and after that, we find the transformation. This transformation is 3 by 3, if you remember. This is 3 by 3 matrix to find the transform matrix from these 2 points to these 2 points. And after that, we try to warp this image to the new coordinates. That's here. This is a matrix 3 by 3. I can show the A by N for you. That is 3 by 3 matrix. And after that, we warp the original, the input image by using the transformation, this transformation, and we got here the warp image, we also need to have to define the size of the image, because if we don't resize the image, the output should be like have some border around. We can also see this kind of this book, right? The cover of this book, but around is something. So make sure that we want that the cover of this book can be the full picture of the output. Okay. It's okay. Do you understand here?
Yeah.
Yes.
Okay. Okay, this is the other example for the perspective transformation. We have the picture here, and this is the book in the picture, and we also caring about three corners of the image here, right? So let's see what this example want to do. We have the first image, that is the desk perspective. That is the second one, and we have the other image, that is this one, and we connect them to each other. So this is the book, and this is the book on the desk. And this example, what they want to do is that they project this book into this area. And how can we, because this one is like just the rectangular, right? We want to project directly this one into this one.
So
And
reverse, right? It but reverse, right? From normal to this area, right?
yes, we would like
Okay.
to project, in other words, we would like to project this book into this area.
Okay.
Yeah.
Okay.
Yeah, and with the same method, first one, we need to find 4 points, right? This point. Okay, let's draw here. We would like to find this point here, and we project how to transform it into these 4 points. They also have some way to detect the points, but that's why we indicate here already for you. This point have this is the corner perspective. That is the point in the new picture. We indicate for you already. So it's actually these 4 points of the new image. And this is the points of the original of the book. So this point is really easy to detect, right? Because if we know the weight and the height of the image, then we can easily to detect the corner. And after that, we have the source of the points and the destination of the points, right? So now we will compute the homomorphism matrix. This is also the 3 by 3 matrix to find the transformation from the input and output. So that's why we can find the homomorphism here. Okay, again, I will show the matrix here for you to see. This should be 3 by 3 matrix. That's the transformation. And after that, what we want to do is that we transform this book by this matrix into the new one, right? And absolutely, it will have to transform this one into this border. Yeah. And we want to visualize for you. Let me recap here. This one is the size of the new image we want, right? Instead of previously we let the new image had no background, because we want to show this one only, but we want the size of the final image should be keep the same. like this one. So we let the shape here. We will let the same height and width of the output. So we can see that the book already projected in the new space, and the background will be 0 because nothing here, so it will be black. And now we need to overlay this image and this image, and the algorithm is just like for those that is 0, right? That is the black. We will replace by the other pixel of the original image. And after overlay that, we can see here. Yeah, that's all. Do you understand? It's okay for you?
So the the point is how do we know the source I mean the
You know,
longitude and latitude. I mean what is the source and that is destination to map that's 4 corner together,
okay.
right?
Yes. This is concept. We have the function here. This is the function here. They usually want to check by click on the points. For example, but this one I already checked. Now Colab not support for this library, but I check on the server. You can download this one and check on the Jupyter notebook. This can be working. Yeah, basically that we will read the image, and it's kind of interactive function. And when you click here, the output will be the position of that point for you, and you will manually detect. Yeah, you can place in the right way like this. You can change the position, but make sure that the source and the destination would be like corresponding with each other. It's okay. Yeah, this link function can help you to detect the position of the point.
So the point is just manually hand pick it for in the destinations. Yeah.
Yeah. Same like in the software, we also hand pick projective. Let's say we capture the one picture and we have to manually stretch it out or zoom it by hand and capture that one and project it.
Yeah, right. Probably in some situations or in some applications, you can probably do this automatically. It depends on the application. So the locations that you want to project something to, probably it can be detect, for example, using edge detections or a line detection, something like that. So you probably be able to get the positions by using those algorithms, so that you can project something onto that area, particular area as well. So that can be either manually pick the areas, or you can do the automatically detect the area that you wanted. Yeah.
Okay.
But at least it has to have 4 points.
At least 2. Yeah, 4 points.
Yeah.
2. At least 2. Okay.
At least 4 points, because the degree of freedom for the homomorphy is 8. So it's divided to 2, that we need to have at least 4 points. So it's like the application of scanning the documents that Dr. Jeff shared last week. If you capture the document from different angle, not directly to the front, it cannot be the right rectangular, right? So it can help us. Yeah, we don't need to manually detect the points. That can help us to detect the edge and the corner And this can, the algorithm also need to also do the transformation for you. And the final one is just the nice documents in the rectangular form. Okay. Okay, let's the last one we need to cover today is the we move to panorama. Should I finish this before the next one, right, Dr. Joseph?
Then what do you mean by the next one?
Yeah, I need to finish this one as well, right? Panorama.
Yeah. Just
Okay.
finish every lab that you prepare. Yeah.
Yes.
So then after this, we'll talk about the camera calibrations. Yeah.
Yeah. Do you do anyone know the panorama? Do you have any application for that? I guess that in the iPhone have the function for that. Do you have ever test that?
Yeah, use a lot.
Yeah.
Yes.
Yeah. Uh, okay, now we let's check for image and see it how does work. I guess that three scenes can be this can be captured at the same time, so we don't see that's so much different, right? That's kind of when we use the iPhone, when we move the phone from the left to right, it actually kind of need time, so it's easier to do the panorama. But let's see. Yeah. Okay. The purpose of this one is that we would like to stick all of the image together, and so that we can have the longer image to capture all of the scenes. Firstly, we also need to use the shift to detect the key points of for image, right? Okay. Actually, the method to do the to do the panorama is that we need to find the key points and the descriptor of all of the scene. After that, we try to match them one by one, and then we transform it into the coordinate of the reference image, and then and finally we will match them together. So shift is used in this case to detect the key points and descriptor. So first of all, find the key points, and then we use the feature matching in the previous lab, if you remember. For the first one, we try to find the match of the first and the second image. This is the match of the two and the third image, and the third and the fourth image. The order of this one, of 1, 2, or 2, 1 is really important, because if we use the matches 1, 2 and let the descriptor 1 as the first one, which means that is the reference to choose the match. As I shared earlier, the number of descriptor in the first image is also the number of match for the 1, 2 here. So if we stay like matchy 1, 2, which means that we consider the first image as the reference image. And this one, we consider the second image as the reference. Okay, after that, we find the good matches. because we only consider the good matches is which the best match is less than the second match around 75%, and we find on the good match for the first and the second image, second and the third image, and third and fourth image. Let's show the first one and the second one. Okay, as I mentioned, the first one can be like the reference image. They try to match the first one and the second one together in the first lab that I said in the morning. And this one is for the second image and the third image. Last one is the three image and the fourth image. And then we use the red set to find the transformation matrix between them. Okay, for the first one, that is the M12, that is the transformation matrix from the first image and the second image. In the next step, what we need to do is that we warping and stitching the image together. Okay, we can start from the image number 4. The reason why we start from number 4 because the final image that I want here is that we will take the first image as the reference image for all of the image. So firstly, I need to start with the fourth image first and try to warp the fourth image into the space of the third image. It is necessary to calculate the width and the height of the panorama. Okay. We will need to find the height and the weight of the third image first, and then the height of the warp image number 4 should be the same height with the image number 3, right? This is image number 3, and this is the panorama width and height. We should have the same height with the image 3. And then we use the warp perspective function here because we want to transform the image number 4 with the transformation matrix that we just calculated. And we also need to define the size of the output, and we got the panorama of the image 4 and 3. Let's see how does this work. This is the panorama. This is the image number 4 already transformed to the perspective of the image number 3. And what we need to do is that we need to stitch the image number 3 to the image number 4 that's already warped, right? Which means that we stick this one to the image 3 in the first image. We will, yeah. That is the output. Actually, that is the kind of this area like the image, the first image, and this area is the warp fourth image, and they stick together. Do you understand until here?
Yeah.
Yes. Okay.
Okay. So now they call this one is the image 3, 4 because it's on match third image and fourth image already. And then what we need to do next is that we again do this one. We warp this one into the image 2. Yeah, we do the same methods. Yeah, and then we stitch the image 2 to the stick image 3, 4. Yeah. So this area, this one, including the second image, third image, and the fourth image. And finally, we do the same way to warp this one into the coordinate of the frame of the first image. Do the same way. And then stick them together. Yeah. So I think for this task, if you see this kind of simple, but when in the practice, I think it should be easy if you need to imagine the order of them first. For example, if they show you these 4 images, we need to find what is the order of them from left to the right. And we should consider one of them as the reference. In this case, we use the first image as the reference, right? And we try to transform all of other image into the first scene. So we do like from right to left. We also do left to right as well. If we and the function, you need to write them in the right position. We also can choose anyone for the reference, but make sure that we calculate the right transformation matrix and the matching as well. I think you can bring this notebook at home, and you can try by yourself to choose the other image as a reference.
So the point that you have for this code is image 1 as a reference, and then when we do the what we call the
Stitching.
create stitching, so
Yeah.
we do reverse 4 and 3 to make a then wrap together with into one image, and then we do that wrap into with 3 again, right? Yes. No, with 2, I think 2.
And in your case, you want the first image as the reference, right?
Yeah.
Yeah.
Yes.
Yeah. We also can do the fourth image as the reference as well, and we transform from the left to the right. Yeah, but make sure that we calculate the right transformation and the right matching.
But how can we smooth the stick region?
You mean this one, right?
Yes, the stick region I can see very clearly. So how can I smooth it?
In the morning class, Dr. Chacha say how we can. There are kind of 2 ways. The first way is he mentioned that we use the window to go through on this area, right? To average the color of the window and we to the middle one, or we can use how to say it, how to call it, I forgot. Like the second way to
It is the weighting functions.
Yeah,
So the weighting functions that you have a pixel that is closer to the edge, getting a lower weight. So it's right at the middles, and then when it started getting close to the edge of the image, it getting lower weight. So you apply these filters of functions to the image, so then it can blend the image much better than just using the average pixel. Yeah.
Yeah.
Okay. So we using a mean filter, average canal.
Yeah, it depends on case by case. So probably in some case, averaging pixel nearest neighbor works, but in some case it doesn't work. So then you have to change the filter functions to, for example, weighted functions. Yeah.
Okay.
So in OpenCV, there is a function that you can use to define what kind of filters that you want to choose to select to apply to blend the image. Yeah.
CV balloon middle filter. Okay, thank you.
Okay, now we also do for the panorama, but using the OpenCV Stitch Flash. Okay, now is the first scene and the second scene. We then stitch them together. Yeah, this is the stitch flash is from the OpenCV. Yeah, to help us to generate the panorama of the input image that we provide to them. So, okay, the other is we have the file image of the like the sun scene, right, in the sea, and we want to do the panorama for that. Load the key image. Yeah. Okay, for the first one, scenario that this one we also consider the first image as the reference image, and we can do the matching in this way. The other way, we can consider the second image as the reference, and we try to transform the first one and the third one into the coordinate of the second one. In this case, if we do like this, that we consider the second image as the reference, we transform the 0 is the first one, 1 is the second, that is the order like the number usually do. And we try to transform the 0 and the 2 to the reference, to the second image, 1 here. To say that. Put them together, and then we warping, use the range function to find the transformation matrix as well. Let me show you the result first and explain later. You see, so for this one, this is the already transform the first image into the second coordinate image, and they already teach the first image and the second image together, but they take the second image that as reference, and then we can have this one. And after that, we would like also to transform the third image into the frame of the one that we just have here, and this is so that we can have the result here. So as I said, that we can choose any scene to be the reference for the transformation. Touch the panorama. Yeah. So the only image that the coordinate of the only image that have the same coordinates after all is the second image, right? It doesn't change anything. For the first image and the third image, they change already. Actually, they transform and then they stick to the second one so that we can have this image. Okay. Do you have any questions so far?
Just play around this one.
Yeah. I think, yeah, as I said, that we need to find the one that we want to keep the coordinate of that, because we take the image. The image can be taken from maybe different views, and or sometimes different camera or different time. So what we need to do is we want to do the panorama of all of them, and the second thing that we should consider is the size of the image, the size of the output as well, because after all, we want that it have on the same scene. So I go kind of quickly for the size, and I think you can read more to know what is the size of the output panorama.
Yeah.
Okay.
So we can this one, if then in OpenCV have the like average filters, or what else? What filter we have studied?
Weighting, right?
Weighting function, and
Yes.
then what else? Blending of weighting.
I guess it's
Yeah.
have. Okay.
I need to do it manually because they in the SNICS class, I think they do it. They apply it already, I think. In the Panorama SNICS, Panorama, which the class?
I remember it have. Let me check.
Yeah, in OpenCV, there's a function called add weighted, right? And then you can add weighted, and then you can specify the alpha value, beta value. So that's the equations that they use to calculate these weighted functions. So then you can control the alpha and beta parameters of those, and then you can use the result to blend the image.
Yeah. Okay.
Yeah. Okay.
Okay. But normally in the iPhone, when we do the panorama, the image becomes so, the size output becomes so, shallow, short, which means that this function, they mapping only like what we call long, like panorama, right? It's long pano, but it's not wide enough. It's depend on the camera, or
No, it
function
depends.
function.
It depends on the size, the final size that they want to keep. So in iPhone, I believe they have a predefined width and height of the panoramas. So that's why if this image is happen in iPhone, they will clip it off. You mean they will crop it off like that. Let me see. I can draw. So they will probably crop this something like that. So something like that. So that's why we won't see this area in the final output. So they define the height of the image, the final image already, and then they also define the width of the image. So it doesn't matter how many image you scan to that one, right? When you doing something like this, So it doesn't matter how many image. So they keep stitching it all together, and then when it reach predefined image resolutions, which mean width and height, yeah. So they just crop it up, and then they crop everything that with a black background over here. Yeah. So yeah. So that's what happened behind the scene actually.
Okay, clear. Thank you.
So any other questions?
Yeah, I guess you should go home and play around this one to see that all of the how does work in Panorama in the basic algorithm here, and yeah, and after that we can explore more technology for that. It's when the how the yeah something like iPhone really do for that. And actually, I guess I say more algorithm behind that for the fusion as well, to so that you can see the output image as kind of pretty. But yeah, the key thing in here that how they do the transformation. Yeah, to make to because if we know that about the videos, it kind of many multiple frames, right? So when we move the iPhone, we never touch or let them know that how many image that you want, right? It's just be the videos, and how can they extract and they extract the frame from that video. That is kind of the number of scene of how we do how we are doing here, and then they use the all of that image, all of that frame to do the panorama.
Okay, here spark me up a question. So the thing is, here we capture the static image, every single image with the big scenes. But in let's say in iPhone, they actually make a video and then they capture one image all together when we do the panorama, and they store in the memory, and then they apply this technique to make a panorama picture, or they use by the video to make that one. What you got what I mean, right?
Yes.
So how many pictures they have, and they store this until, I mean, let's say they predefine the length. I think it's predefine the length in the iPhone or what the application, let's say 4,000 or 10,000 pixel or whatever. Then whatever you can swap, you can narrow slowly, or you can, I mean, you can spanning slowly and you can spanning fast until you reach that 10,000 pixel. What then they just capture every image, and then they make the panorama, right? Is it the way they do?
I guess that when we use the iPhone from left to right, it's kind of video that you are thinking, right? So it's kind of like continuously samples from the camera at the high frame rate. And typically, if there is a term they say that FPS, that is a frame per second.
Seconds. Yeah.
Yeah, it's kind of around like 30 something. So for each frame that it will extract the like narrow vertical or horizontal strip from the center, not the full frame. So this strip can be like warp and align and stick in real time. So it stops when you reach the maximum panorama length. Yeah. Yeah. You can do something very slow, right? But someone's very fast. But as long as it can reach the maximum of the panorama length, that it will be stopped.
Yeah.
And number image, I guess that maybe that no, it's around like I don't know, but it's not fixed. It's based on how we can move.
So basically they still save the static image when we do the pano, and then they make the panorama based on that static image. Even we do banning
No,
video.
it actually doesn't matter whether it's image or video, because the video, it is nothing but a stack of image. All right. So the video that we are moving now, you are not
Yeah.
seeing the video, you're seeing a stack of image.
Mm.
Okay. For example, when we are saying 30 frames per second, so if you are stacking image for 30 frames, that will create a movement, right? That will create a
Yes.
movement. If we move, so which means that, let's say that I move my finger from here to here. All right, that's the movement you see. But actually what the camera see, it is just taking a snapshot, one image at a time, but it's very fast. It's 30 frames per second. So when we put all these frames together, it's create a movement. So that's what we call video. So its video is nothing but a stack of frames.
Mm.
All right, 30 frames per second it's not that fast, but it's fast enough for our eye to interpret a movement.
Yeah.
All right. Let's say that if you let a camera capture a video for 2 seconds, which means that you have 60 images that you can extract from that. Yeah.
Yeah.
So within this 2 seconds, it doesn't matter how you move. There's 60 different images. So then we just sample probably 2 or 3 images from there and then stitch them together. Yeah, that's it. Yeah.
Mm.
Mhm.
Okay.
Yeah.
Yeah.
Yes, that's a pretty nice example. So I
Definitely.
think, yeah, that's all for the lab of panorama that I covered today, Dr. Joseph.
Yeah, thank you, Yi. It's pretty good. Thank you very much. So another way of thinking about the video would be if you watch a cartoon, right? So the cartoon, that's the way they created it. So they start drawing one page at a time, right? But small different change. So then when you make that piles of image moving very fast, it will create a movement. So that's the same thing. Yeah, that's the same concept for the cartoon. Yeah.
Yeah, that's it. Animation. They draw it by hand.
Yeah, right. That's how the cartoon has been created in the past. Yeah. The cartoon, the animation, or stuff like that. All right. So now let me introduce this a little bit. Let's say like 20 minutes, and then we'll take a short break and then come back with this one. So for this lecture, there will be a lot of mathematics. I would say it's a lot of mathematics about camera calibrations. So what I'm going to do is trying to simplify it. Okay, so I'm not going into very details of the mathematics, but I will give you an idea, like what it is, how it works, why it is something like that, why this happened, why that happened. All right. So, but you will see a lot of mathematics in this lecture, because it's all about mathematics. Okay. So now let's begin with camera calibrations. So in this lecture, we will learn about the linear camera models. How can we calibrate the cameras? What is intrinsic and extrinsic camera matrix, and what is the simple stereos, and then we will talk about the uncalibrated stereo. So we'll discuss about the epipolar geometries, how to estimate what is called fundamental matrix, and then finding some correspondence, and then how the depth can be created. So why do we need to calibrate it? Why do we need to know about the camera calibrations? So especially if you are working in especially, for example, in robotics, in computer visions for inspection, something like that. So camera calibration is the heart of those applications, you know. So here's the example of one of the sensors, that is the Intel RealSense. It is a serial cameras that it can be used to capture the 3D informations, for example, the depth map, the point cloud, something like that. So this camera is very small, you know, it's very small, something like this, and then you can mount it into the UAV, the AGV, or AGV stand for automated guidance vehicle. All right, so you can mount it into that, and then use these cameras to capture the environment. So in these cameras, it constructs something called serial cameras. So it has 2 cameras. So as you can see from here, there are 2 cameras actually, which is the RGB cameras. And then it is also have the source light sensor. So these 2 camera, before it can calculate, or before it can capture a point cloud, or it can calculate the depth map from the scene, it has to be calibrated, right? It has to be calibrated because the camera, the image that you capture is from 2 cameras, and then you want to calculate some points in the scene to the camera itself. So you need some sort of triangulations equation to calculate the distance between the camera and the objects. And you use 2 cameras to determine the distance, which means that these 2 cameras has to be calibrated. It needs to know how to transform one point in one camera to itself. So it needs to know each other's. So this is one of the example of the application that camera calibration play an important role in these applications. And another applications, like I mentioned, which is in robotics. For example, if you want to perform the bin picking, right? So you can either mount cameras into the robot hands. So this is what we call eye in hands. Okay, eye in hands. So if you look at this robot's hand, so this is Intel RealSense camera mounted onto the robot's hands, or robot arms over here. So this is what we call eye in hand, because we add an eye to the hand. So this kind of example you can use to, for example, scan things, or you can mount a gripper, and then along with the cameras. For example, you have a gripper here, and you mounted a camera here. So when the robot it moves with the eyes, right? It moves with its eyes to pick it up something, to pick up something. And another application would be you put a cameras not on the robot's hands, but you put camera outside. For example, this is what we call a robotics vision guidance. So instead of just mounting the cameras to the robot arms, we are mounting the cameras to some sort of fixed stand, for example here, or we mounted a camera here, or we mounted a camera here. So this sort of cameras we can use in a bin picking applications, something like that. So these cameras has to be calibrated with respect to the robot, right? With respect to the robot's coordinates or the robot's positions, so that the robots can come into a conclusions that what it sees and the locations of that object with respect to itself, where it is in the environment. So if you don't calibrate, so the robot won't be able to calculate for the positions of the object, so that it doesn't know where it should move to, how much the joint angle each and every joint of the robot should extend. So that's why we need to calibrate the data. Calibrate the camera with respect to the environment or the robot itself. All right. So this is another applications. And another application would be, for example, in the inspections. We can use a multi-camera setup for inspections. For example, you have a very large piece of equipment that you want to inspect. For example, this flat object. But using one cameras cannot cover the entire area of the objects. So you need a multiple cameras. So you need to be able to calibrate these two cameras, and then you need so if you do not calibrate these two cameras, you won't be able to stitch the image from different camera together. So the calibration here is like we're finding a homography in order to translate or in order to transform the image from one camera to another camera so that we can stitch them together. So these are another applications of why do we need to do the camera calibrations, all right? And another applications would be in the form of self-driving car, all right? For example, if you mounted a sensor, it's either the cameras or the LiDAR sensors. So we have to calibrate the sensor with respect to the car, so that the car know exactly what it see, with respect to itself. Where is that object in the environment? All right, so we need to calibrate so that everything is in the same coordinate. All right, so that's why we need to calibrate the camera with respect to the body of the car, so that every object, every pixel is in the same coordinate with the car itself. All right, so this is another applications of camera calibrations. All right. So let first start with a very simple and important types of cameras. So we call a linear camera models. All right. So let's look back at the first lecture that we talk about a pinhole cameras. So in the pinhole cameras, we have these objects, right? We have a world coordinates, which is a scene coordinates, and then we have the camera coordinates at the locations of pinhole, right? And then we have the image plane, where we are going to project a point in 3D onto this image plane, which is 2D. All right. Going from 3D point P, project to the image plane, going from 3D to 2D. So this is what we call forward imaging models. So what basically we are trying to do here, we are trying to project or mapping a point P over here in world coordinate, which is 3D. So point P here can be represented as a coordinate X, Y, Z in the world coordinates. So what we are going to do is that in order to create an image, we have to project this point P from 3D onto the image plane here, which is this point here, which has a coordinate of X and Y, X, I, Y, I. All right, so that's what we call a forward imaging models for going from 3D to 2D, passing through the camera coordinates. All right. So in order to find the locations of the point P in image planes, we need at least two transformation to going from a world coordinate to camera coordinate, and then we go from camera coordinate to the image coordinate until we get the coordinate X, I, Y, I over here. All right, so going from world coordinate to camera coordinate is still 3D to 3D, right? Going from XW, YW, ZW, which is point XW here, a vector XW. So we can translate or we can transform this world coordinate to camera coordinate so that we can get a vector of xc, which is xc, yc, zz. And then we can map this vector, 3D, three-dimensional vector to 2D so that we can get a point P in the image plane, which is at the location xi, yi. So we need these two projections, or we need these two transformation. So going from world coordinate to camera coordinate, we call this coordinate transformations because it from 3D to 3D. And then if we go from 3D to 2D, here we call perspective projections. So it's like homography. So we already discussed that, right? So these are the how we can going from 3D to 2D. So let's first work back from image coordinate and camera coordinate, work backward. Let's first see how can we project the point from camera coordinate onto the image coordinates. All right, so from the projective from the perspective projections equations, we know this equations already from the first lecture, right? So we know that we can get the point at location xi, yi. Xi is equal to the f, which is the focal length, which is the distance between the pinhole and the image plane. So the xi is equal to f multiplied with xc divided by zc. So which is zc is the vectors from the pinhole, right? From the camera coordinate frames. And similarly, yi is equal to f multiplied with yc divided by zz. All right, so this is how we can going from camera coordinate frames to the image plane. All right, and so in image planes, right? Image plane, we are talking about the unit in millimeters. For example, the image plane is possibly nothing but it's just the size of the sheet of paper in millimeters, how big it is, right? But if we want to project this image plane to a sensor, right, which is in terms of pixel, right? So we can, how can we project that? So we can define that if my and mx are the pixel density, so how many pixels per millimeter here, right, in x and y directions of the image plane. So we can say that if we map this point in the image plane to the image sensor, we can use these equations to transform any point in image planes to the image sensors. Okay, so the pixel locations in image sensor, you can calculate it from using mx multiply with f and then multiply with the ratios of xc and divided by zz. All right, similarly for the y. So the m and y is unknown and it is part of the calibration process. So we need to find this, whether how many pixels, what is the pixel density, so that we can project any point in image plane to the image sensor. Right. So and we usually in the image, as I mentioned, we usually treat the top left corners of the image sensor as the origins of the image, right? When we are talking about the pixel at location x0, y0, we are talking about the top left corner of the image, right? So the thing that we need to find is what we call a principal point. So a principal point is the point in the middle of the image. So the pixel, the central pixel. So that's what we call principal point, which is at the locations or x or y. All right. So we can project any point from image plane to image sensor, the locations in image sensor, by using these two equations. All right, these two equations, u is equal to mx multiplied with f, which is a focal length, multiplied with xc divided by zc, and then plus the principal point ox and oy. So that's how you going from image plane to image sensor. That's how you can map in millimeter to the pixel, right? So if you put it all together, and then you can simplify mx multiplied with f, you can simplify this, and then you can just simplify them to fx and then my f into fy. So we can say that fx, fy, ox, and then oy. So we call these intrinsic parameters of the cameras, right? So this is what we call intrinsic parameter of the cameras. Okay, so as we know that the perspective projection is nonlinear, so it is more convenient to express them as a linear equation, so that it is easier to calculate, right? So I think let's take a short break here. So then after we come back, we'll talk more about the perspective projections. How can we like calculate the calibrations process over here? All right, so let's come back at 2:37, right?
Okay.
All right. I hope everyone is back. All right. So let me just continue here. So let's discuss about the perspective projections. So let's first talk about the homogeneous coordinates here. So the homogeneous representations of 2D point. U is equal to UV here, which is equivalent to the 3D point, which is the point U in coordinate homogeneous coordinates, right? The third coordinates, which is the tau, the W tau here, is not equal to zeros, right? So which means that going from Cartesian's coordinate, that is we have the point U and V, which only two coordinates, right? So we add the third coordinates, which is the W. So the reason why we add this one, because as we discussed earlier last week about the translations, right? In order to perform a translations of any points in the image, in order for us to perform a matrix multiplications to perform a translation, so we need a third coordinate. So that's why we convert everything from Cartesian coordinate to homogeneous coordinates. So what it says here is that, let's say that we have a plane U and V, the gray area here, the plane, at the coordinates in coordinate of U and V over here, so which is in Cartesians. So we are saying that we create another coordinate U tau and V tau over here, and then the plane, the gray plane here, is lie at the W tau is equal to 1, right? So this is how we add the third dimensions over here. So we are saying that any point along this vector L, which is originate from the originals of this plane, U tau, V taus, any point in here is equivalent to the point U over here from the Cartesian coordinates. All right. So which means that it does not matter how you move. So it just the W tau here, it's just the scaling versions of that point in homogeneous coordinates, right? So we can represent the point U in Cartesians by using this vectors of U tau, V tau, and then W tau. Okay, so basically we can set the W tau is equal to 1. So yeah, that's it. So so that we can say that the homogeneous representations of the 3D point X, which is in Cartesian coordinate, which is point X is equal to coordinate X, Y, Z in 3D coordinates, can be represented in a 4D, right? Because we added another coordinates, that is the W tau. So 2D points in Cartesian's coordinates can be represented as a 3D point. So we add the W, and the 3D point can represent it as a 4D point in a homogeneous coordinate. All right, so we add one more coordinates to the Cartesian coordinates. All right, so from the perspective projections equation here, so after we added it, and then we simplify this, and then we replace, for example, we have this vector, right? U, V, and 1, which equivalent to the U tau, V tau, and W tau. So any Z over here is just scaling functions, right? So we can substitute the value of U, which equal to these equations. And then we also substitute the value of V, which is equal to this one. And then we finally get this matrix. A matrix consists of Fx, Fy, Ox, and Oy. All right, so So that's matrix. What is matrix that this matrix represent? So if we look at this 3x3 matrix in the orange over here, right? So this is what we call a calibration matrix. All right. So which means that going from any point xc, yc, and then zc. So if you multiply this point in a camera coordinates, you can find projections of the point in the image plane by multiplying that point with the calibrations matrix. So, and then if you look at a hole in the red rectangle here, so this is what we call the intrinsic matrix. All right, so this is intrinsic matrix. So because we are transforming a point in camera coordinate to the point in the image plane, which means it's inside the camera. It's inside the camera itself. So which means that's why it's called intrinsic matrix, because it's inside the camera. So it is the parameters or the matrix of the camera itself. So that's why it's called the intrinsic cameras. And then if we look at only this 3x3 matrix here, this is called the calibrations matrix. All right. So we can represent it as a K. And this matrix have a characteristic of the upper right triangle matrix, because this lower is just 0. So the upper would be fx, 0, ox, fy, and oy. All right. So this 2f is just the effective focal length of the cameras. All right. And the O is just the principal point of the image plane, right? And together we can construct the intrinsic camera intrinsic matrix mint by simplifying K and 0, because the last column here is just 0. So we can simplify this form, the form of these intrinsic cameras to K and 0, right? So this is what we call intrinsic matrix. So projecting any point in camera's coordinate to the image. So that's happened inside the camera itself, okay? So now what we get now is that we are projecting any point in this coordinate, in this camera coordinate to the image plane. So we got this intrinsic camera intrinsic matrix, which is performing a perspective projections, right? So that's what we got. Now next we are going to consider how can we project this point in a world coordinates to the camera coordinate. All right. So to complete this cycle, so that we can project any point in world coordinate to the image coordinate. So the second part would be how can we project any point in a world coordinate to the camera coordinates. All right. So to find the positions of point P over here with respect to the camera coordinates, how we can do that. All right. So we can see that the positions of a vector CW over here and the orientation R of the camera in the world coordinate frame W are the camera extrinsic parameters. So which means that these are the parameters from outside the camera. All right. So which means that we are transforming something from outside camera to the camera itself. And then inside the camera, we call that the intrinsic parameters. So that's what we saw earlier. All right. And so which means that going from world coordinates W to the camera coordinates here, so we need a rotation matrix to rotate the point or to translate the point within these coordinates, right? So actually, so I think I'll skip this for simplicity, just to give you a rough idea that as we discussed that the extrinsic parameters consist of the R and the vector CW here of the cameras, so that we can construct this matrix, right? R1 to R33 plus the translations, right? We have a translation. So in order to translate or in order to transform any point, we need both rotation and translation matrix, right? So for example, from any point XW, we want to find the projections from world coordinates to the camera coordinate. We need the rotations of that point plus the translation. So this two operation is a must, right? So we can rewriting this using a homogeneous coordinates. So we're gonna get this rotation. I mean, we're gonna get this transformation matrix. So we get this. It looks like what we call a homography, right? This is the homography or perspective projections, right? And which are mainly that are the rotation matrix. And here, the last vector will be a translations. So if we multiply these transformations with a point in a world coordinate, we are going to end up with a point in a camera coordinates. All right. So we can simplify this matrix as this form, which is R 3 by 3, and then 0, 1 by 3, which is the last row here. And then with the translations over here, and then 1. So this is what we call the extrinsic matrix, which means that going from world coordinates to camera coordinates, that is the X outside of the camera. So that's why it's called the extrinsic matrix, right? So that's how we going like from world coordinates to the image coordinate, using these two matrices, extrinsic parameters and intrinsic parameters. So I think, what time is it? Okay, let me see. So let me talk about what is the procedures of camera calibrations. All right. So the first step, if you have any camera or two camera, the first step is to capture an image of an object with unknown geometries. So for example, here we have the objects of unknown geometries. So we know the width and the height of these objects. We know the size of each grid in here, right? So, and this is the capture image of that objects. And then next, we will identify the correspondence between the 3D scenes point and the image point. All right. For example, the point, the purple point here, this is a point in the 3D scene, right? And then on the right-hand side, and the purple point here, so this is the point that is correspondent between the 3D scenes and the image that we captures, right? So probably this point is at locations within the 3D scene. It would be at zeros, and then Y would be probably 3 inches, and then Z would be probably 4 inches, for example, in the 3D world. And then the point purple here, it probably have a coordinate at pixel number 56, and then the pixel in V coordinate would be 115. So that this is the positions of that. So we find this many correspondent. For example, we have point yellow, point blue, point red, something like that. So we find this correspondent between the real objects and the image that we captures. And then for each corresponding point I in the scene and the image, we can, so we know like how to map them. So this is look like the homographies or perspective projection that we did before, right? So we have this unknown matrix that we want to find out, and this is the coordinate in the 3D scenes. and then we want to map this into the 2D scene, right? So it's like the projection matrix. So we can just calculate this using these equations of constraint least square, like we discussed before, right? So we have the known matrix here, and then we have the unknown matrix P, right? So before, what we have seen is A of H, right? A of H, but now H, instead of homography, is turned to projection matrix H of P. But the concept is very similar, okay? So let me just skip this. So the concept of this is nothing but it doesn't matter how you scale the scene, how you scale the objects. When you capture the image with the same projections, so you're gonna get just a scale versions of that scene. Yeah, that's the scale of projection matrix means. Yeah. So I think this one it's kind of similar to the equation that we discussed in homographies in stitching matrix. So the equation look very similar. It's how we solve the constraint least square to find the matrix of P, right? It's H before. So that's how we find the projection matrix. All right. So and how can we find the intrinsic and then the extrinsic matrices of the cameras? So as we know that going from world coordinates to the image plane coordinates, right? To the image coordinates, we need to matrix that is intrinsic and then extrinsic. So the matrix extrinsic parameters here take you from the world coordinate frames to the camera coordinate frames, and then you multiply again with the result of that with the intrinsic parameters, intrinsic camera parameters. It will take you from camera coordinates to the image plane coordinates. All right. So if we simplify this one, we're gonna end up with K and R. So R is the rotation matrix, and K is the upper right triangle matrix over here. Right. And if you look at this P, right? If you look at this P, the last column over here, that's the translation. So then we can find this translations by using the inverse of this K matrix over here. That's how we find the translations. So, and another parameters that could have some effect on the camera calibrations would be the distortions of the image. So we are not considering here, but just keep in mind that we have this distortions coefficient. That is the object just slightly whether it's moved a little bit from its original position, it's either radial distortions or it's tangential distortions, right? So let's look at the simple camera projections, the simple stereo, right? So given that you have calibrated cameras, can we find the 3D scene point from two image. All right. So like I mentioned before, if you use the Intel RealSense camera, which have two cameras, capture two image. So by capturing two image, Intel RealSense, it can calculate the distance from the cameras to the point, any point in the scene. So how can we do that? Or can we do that? Calculate the 3D scene point by using just two image. So how can we do that? All right. So let's say that you have the one camera sitting here, and then you're taking the image of the scene, right? And then you project. So you're gonna end up with having some point UV in the image plane here. All right. And then so let's assume that you already calibrated your cameras. You know the intrinsic and then extrinsic camera parameters. So you know the equations going from 3D to 2D, and you also know the equations going from 2D to 3D, which is this one. So assuming that you know all these parameters, right? And then what you're going to do next is that you have two cameras sitting apart, right? You have two camera 1 and then camera 2. So they are sitting apart at B dimensions, at B meters. So you have these two cameras sitting apart from each other at B locations, all right? Let's say that, for example, 10 millimeters, something like that. So this is what we call a horizontal baseline, okay? So by using these two image, and then we know the intrinsic camera parameters. We know the intrinsic camera parameters. We know fx, we know fy, and then we know the distance between the two cameras, the b, and also we also know ox and oy. So we can substitute this value into the perspective projections equation, so that we can end up with the value at the 3D scene. All right. So yeah, you just calculate this one. All right. So this is the example of simple serial cameras. So in real sense, it has the left and right cameras. So the horizontal baseline over here. So this is the right cameras, this is the left cameras, and then this is the B value of that one, which already known to the cameras. So then when taking the image of the scene, when taking any image of the scene, so we can know for sure that some point in the scene that these two camera captures, we can use the triangulations equation to find the distance between the cameras and this point itself by using the previous equations. So that's how we can use some sort of stereo cameras to calculate the depth between the image and the camera itself. That's how the depth image can be captured. Okay. So I think I'll pause here because there's too much mathematics. So I'll walk you through how can we actually calibrate the cameras. Okay. So you can go to this tool and then download this to file. All right, so I have the file called calibrate cameras, and then I have the file, a script called generate a shadeboards. Okay, so why do we need a shadeboard? Like I discussed, right? To calibrate the cameras, you need a known geometry, right? You need a known geometry, the object with known geometry. So you need that one. Okay. So this is the shadeboard that so here's the shadeboard which generated by this gen shares script. So it is going to gen a shadeboard of 7 rows and 10 columns. All right. And then the size of each square would be 200 pixel. So after you run this script, you're gonna end up with this shadeboard. All right. So if you have a printer at home, maybe you can print this out. All right. And then to calibrate the cameras, because for example, in the web cameras inside your laptop, you don't know their intrinsic parameters. If like the manufacturer didn't tell you, you don't know that, but we can calibrate and then we can extract these informations by using the script. All right, how we can calibrate here. All right, so the first thing first here in the code. So if you download that, all right. So let me show the result first, how it looks like. Let me just pause here and then I will run the script. Oops, give me a second. Right, so we can run UV, run calibrate the cameras. Give me a second. It's trying to connect to my my iPhone. Right, so if we run this one, so what it is going to do is if we show this to the cameras, so it will try to capture different angle view, right? So what we have to do is we have to keep moving this sort of chessboard. So then we are going to use this for calculating the cameras. So what it does here, it trying to detect the patterns inside the inner areas of this chessboard. So this one is trying to capture 20 images, I think. Yeah. So now after we have captured, if you see, after we have captured this, after we have captured these 20 images, and then we perform the calibrations, and then we will end up with this matrix, as you can see. So the last row will be 0, 0, and 1, right? So if we go back to this, the last row will be 0, 0, right? So it will be corresponding to, as the intrinsic. The intrinsic. All right, so you will see here the last row, which is this is calibration matrix, right? That we are finding. So the last row will be 0, 0, 0, 0, 0, 1, and then we have 0 over here, right? Which is corresponding to these elements, and then this 2, 930.09 something here is fx, right? Is fx, and then this 929.289 here is fy, right? Is fy, and then this element will be 0, and then this elements 623 point something, and then 331 is OX and OY. All right, this OX and OY. So by looking at this, all right, by looking at this, 623 and then 331, we can roughly estimate the size of the image or the resolutions of the image, because we know that OX and OY is the middle point of our image, right? Is the middle location pixel in our image. So this is the point at the middle, so that we can roughly calculate the size of the image, right? So which means that it will be the double of this value, which means that my cameras has a resolution of 1200 something pixel in X directions, and 660 something pixel in y directions, right? Because the middle point is 331, so which means that the full length would be 600 something, 660 something. So by knowing this, we know that the resolutions of the image of our camera, we can estimate a rough resolutions of the cameras, right? And this one is the fx and fy, which is the mx multiplied with fx. So which means the density, the pixel density multiplied with focal length of the cameras. So this is what it means, these two value. And also the cameras has a distortions, right? So it has some distortion. So in this process, we also calculate that. All right. So this help us by using this matrix. Later, when we do the AR augmented reality, so it needs these parameters to project the image, right? To project the image, because we want it to be more precise projecting this image. Without knowing these intrinsic parameters, the projection will be huge errors. All right. So what do I mean by that? Let's just run this for a second.
How many image is enough for the intrinsic estimation?
So basically, the more is better. The more number of images is better. But basically, we take like roughly 15 to 30 image is enough here. So what I personally did is I will start with 15, and then I will keep increasing. I will keep increasing the number of images that we have to capture, and then look at the parameters here, whether how much they change. If they stop changing or if they change very small, I'll stop at that number. All right. So here we just like come up with some magic numbers, 20. Yeah, you can probably change, increase or decrease this number to see whether if it's 15, and then if it's 20, if it's 30, is there any improvement in terms of this value? Okay. So let's see why do we need this why do we need these camera calibrations? So like I showed you before, so without calibrating this, doing the, let me see, AR. All right, so because this one pattern, these patterns is also needed to know the camera calibrations in order to project the cube onto these papers, onto these patterns. So without knowing this one, probably the errors of projecting this cube onto this pattern would be very errors, right? Errors will be very large without calibrating that one. Or the tracking will be errors a lot, right? So that's why we need to calibrate the data to know the intrinsic parameter first before doing this AR/VR, right? We need to know those parameters first. All right, so that's why we need camera calibrations. All right.
Okay, to do that, which means that all of the image should be captured on the same camera, right? So
Yeah.
okay, in
Yeah,
case we have like many images, but we actually don't know that how many cameras has been used for capture on of that image. Can we do the same method to do that, or other solution?
Can I get your? I don't get your questions. Can you say that again?
Okay, so in this scenario, we are trying to capture many images, but the same camera to estimate the intrinsic information, intrinsic parameters. But in case that we have like also many images, but can be captured by different cameras, let's say 2 camera or 3 camera, can we do the same method to estimate the intrinsic information, or we try another solution?
We can do that, but that will be in the form of so if you capture the image with 2 camera, let's say, so that will fall under the category of what we say the stereo cameras. All right. So this one. So if you're capture the image using 2 cameras, but you have to set up the environment. You have to set up the cameras in the form of the stereo camera in which, so you have to set up something like this. You have 2 cameras sitting apart from each others, and then before this camera being shipped, they have to calibrate it first, right? They have to calibrate because otherwise you won't be able to calculate or project the image and then calculate some other information such as distance, for example. So you have these 2 cameras and then pointing to the chessboard, into this chessboard. So you capture this many image with these 2 cameras. So what are you ending up with is the intrinsic camera parameters and extrinsic camera parameters of this 2 camera system, right? Of this 2 camera system. So if you are using one image, I mean, if you're using 1 cameras and then you calibrate that one, you are working with single camera system, not stereo, just single camera system, to get to know the characteristic of that particular camera. But if you are using more than 1 camera, let's say typically we are using 2 cameras with the known distance from each other. So this is called a stereo camera system. All right. If you are capturing the image and then calibrate in this system, so what you get is the intrinsic parameters of this system, not a camera, but this system. Okay. So we can look at 2 camera as a whole. So that's a system. If we have 1 camera, so that also as a whole, that's one system. All right. So that's how you can calibrate this, and then you will end up with this fx, fy, b. So when you have a stereo camera, right? When you have a stereo cameras. So when you have a stereo cameras, basically what we know for sure, so is B, right? The B. That's what we know for sure because we set up that. We know how these 2 cameras setting apart. But the thing that we don't know at that point is fx, fy, ox, and oy. That's what we don't know of this system, of this whole system. So the calibrations method giving us these 4 parameters. All right, so that we can use this within the projection matrix, so that we can like project any point in 3D to 2D, something like that. Okay.
Okay, so which means that we can estimate the intrinsic parameters of the camera system, right?
Yeah, right. So even though we have 2 cameras, it's not either one, it's the whole system itself. Yeah.
So the point you do the calibrate the camera. So you put the picture the camera in front of the node the node
The non-geometry.
the node geometry, the one that you draw with the chessboard, right? when
Mhm.
you know the measurements, everything, and then you calibrate it. The camera, you got the the matrix,
Mhm.
eccentric
intrinsic-
matrix,
Yeah.
and then that's in which means that the camera know that area only.
Yeah, it's know that it know this area only. It's know this area in size only. So when we capture different from viewpoint, right? So
Yeah.
we're gonna get different candidates. I would say the candidate point. So this is so we know every pixel in here how they space apart, right?
Space,
Because
yeah.
we know the geometry. So from this point and then this point. So we can calculate the transformation between these two viewpoint because we know this one. So we can
Yeah.
calculate that the transformation matrix. It's it's very similar to how we calculate the homography because the homography we just find the corresponding point between two images, right?
Yeah.
So this one as well. So we capture one image and another image. So we got so we first find the feature points in each image and then match them together, and then find the corresponding find the transformation matrix between the two. So we keep repeating this 20 times until we find a perfect transformation. It's very similar to what we did with finding homography. Yeah.
Okay. So later on for your AR, you also do the area that you calibrated, right?
Yeah, so for the AR, we first need to calibrate this camera first, and then we gonna get this calibrations matrix, right? So for the AR, we need to load this calibration matrix. After calibrations, we are loading that. So in this matrix, we have the intrinsic matrix, and then we have a distortions, right? As you can see here, we have also a distortion calculate these distortion coefficients as well. All right, so we are loading that these two matrix, and then using this matrix to do the AR augmented reality as well.
Yeah, that's for this one you use another chessboard. Let's say another chessboard to do the calibrated, right?
No, it's not for this one.
For the AR thing. Sorry.
Yeah, for the AR, this is not for the calibration. It's for projections. It's for projections.
But the projection should be on the no plane. You do the calibrated?
No, so we
Okay.
calibrate with this one, right?
Uh-huh.
We calibrate this one. Now
Yes.
we know the intrinsic parameters of the cameras.
Yes.
And then next, we want to project anything to
that plane.
to these planes.
Yes.
So we just need some known patterns or known area that we want to project it to, so that we allow the cameras to find these patterns and then project to this.
Oh, okay.
It's just to finding the place to project something onto it.
Yeah, got it. Oh, okay.
Mhm.
Now I got it. The chessboard would help you to draw the information of the camera to get it extrinsic
Yes.
thing.
Yeah.
It's already there, but right now you draw that information out. I think it's in the factory do things already. Now you should know this one by the code to understand this calibration eccentric matrix. Okay.
Yeah, so if we are the manufacturers of the cameras, we don't need to calibration because we know these parameters, but we are not we don't know that, so that's why we need to calibrate. And then to project some objects onto some place in this 3D worlds, we need some another patterns so that we can project from there to these patterns. So it is called this AR board. So it's called AR ARU code marker, right? It's called ARU code marker. So it can be generated as well. So then, yeah, it just needs to detect the patterns and then project the objects onto that.
Yeah,
Mhm.
clear. Okay, got it.
That's right. So that's this is what we call the calibrated stereo, which means that we can calibrate it. All right, we can calibrate, we can find the transformation matrix between the cameras. All right, so that's why we calibrate the camera first in this case. But there's another case where let's say that there's another case that let's say you are walking around some you have this object. Let's say you have this mouse, and then you want to reconstruct a 3D shape of this mouse, right? So what you can do is that you are taking the image from different viewpoint. With the same camera, you're taking the image from different viewpoint using the same cameras. So the question is, how can we calculate the depth, right? The depth, which means the surface from the cameras to the surface of the object. That's what we call the depth. How can we find this depth information? All right.
Z.
Yeah, that's Z. Yeah, exactly. Yeah. So this is how we call uncalibrated stereo, because we are not calibrating the cameras, right? That's why we call uncalibrated stereo. All right. So let's first discuss about the problem of uncalibrated stereo. So let's say that we are having we need to compute a 3D structures of some scene, right? 3D structure of some scene from two arbitrary view, which means we are taking from any point. All right. For example, we are taking this the image of these objects from the left cameras, and then this is from the right view of that. And let's say that we already know the intrinsic of these cameras, the cameras that we are using to take the image. We know the intrinsic parameters, all right? We know from this. So let's say that we know the intrinsic parameters of these cameras. Otherwise, we need to calibrate this camera first, right? So we know the intrinsic of that. So the thing that we didn't know is the extrinsic, which means that we didn't know the transformations from the 3D scenes to the camera. All right. So the intrinsic is from the cameras to the image plane. So we already know that. But the things that is missing is the transformations from the 3D scene to the camera itself. Right. So we have three space. We have world coordinates, we have camera coordinates, we have image coordinates. So now we know from cameras to image, but what missing is from world coordinates to camera coordinates. All right, so that's the intrinsic parameters that are unknown to us. Okay. So how do we do that? First we assume the camera matrix K is known for each cameras that is intrinsic. Okay. That is the calibrated matrix. So the second step we need is to find a corresponding point between these two images that we take. Right, we need to find a corresponding point. So to find the corresponding point, we can use what we already learned, like SIFT, right? So we can use SIFT to detect to find the corresponding point between two images, right? So we can find a set of corresponding features, at least eight point, all right, at least 8 point from the left and right image. Let's say that this image we found this corresponding features point from the left camera and right cameras. And then after find after we found the corresponding point, what we need to do is we need to know the rotation and translation between these two viewpoints. All right, because we want to map them, we want to know exact location. We need to know the translations and rotation between these two viewpoints. So that's what we have to find the relative camera positions T and the orientation R. All right. So how do we do that? So in order to do that, we have to talk about the concept of epipolar geometry, right? What is the epipolar geometry? So let's talk about epipole. So what is epipole itself? So epipole is the image point or the image point of the origins of the pinhole of one camera as viewed from other cameras, all right? So for example, if you are standing at the right camera origin here, let me use another color. Let's use purple. All right. If you're standing here and then you look at these left cameras, all right, what you see, the origins of this appear in your view, which is this point. So this is what we call epipole. If you are standing here and looking to the origins of the right camera, the point that this origin appear in this image is called epipole. So that is EL and then ER. So this point, this is what we call epipole. All right, so that's the first thing we need to know. And next, we have to define the epipolar plane. So what is the epipolar plane? Is the plane that formed by the origins of the two cameras, OL and OR, and the epipole passing through the epipole here. That is the vector, the light blue vector here. And then the scene point over here. This is the triangle here, that's what we call epipolar plane. All right, so this is the epipolar plane. So every scene point lie on a unique epipolar plane. So the scene point is point P over here. All right. So now we know epipole, we know epipolar plane. All right, this is epipole. And then if we look at this triangle, so that is the epipolar plane. All right, so then we can use the epipolar constraint to find this sort of, so what we need from here, is we need the translations and orientation matrix. All right, we need translation and rotations. So the objective here, what we want these two terms. We want these two because we want to know the image that is taken by the left cameras and right camera, how they are related to each other. So if we want to translate this point from the left image to the right image, so we can use the translation and rotation so that we can map any point from here to here to find whether they are the same point or not. So that's the objective. Okay. So this is what we want to find. So we define that a vector normal to epipolar plane. So this is what we call a vector normal. All right. This is a vector, a normal vector. So a normal vector is nothing but the cross product between translations and the vector XL. So a vector XL is nothing but a ray that is going from a pinhole of the cameras to some point in the scene. All right. So a normal vector can be defined as a cross product of translations, the cross product between these two. All right. So that's what you end up with, a normal vector here. All right. So if we are doing a dot product of this normal with this XL, all right, with this XL, so it has to be equal to 0. All right, it has to be equal to 0. So that we can say that we can substitute this dot product XL multiply with this normal vector, right? Multiply with this normal vector XL dot product with this vector dot product with this vector. It has to be equal to 0. So this is the equation that we end up with, because we can substitute this value into this one. Okay. So after rewriting something, I'm not going into this detail. Okay. So after rewriting this into refactor the equations, so we are ending up with these equations, that is XL is equal to rotation matrix multiplied with XR plus translation matrix. All right. So if we go back to the previous slides, this is XL, this is XR, all right, and this is translations and rotations. Oops. How do I clear this? Okay. So if we want to find the point like XL, so we can multiply the point XR with rotation matrix plus translations. So if we look at in the form of matrix, we're gonna get this matrix going from the point, from the left image to the right image. You can use this rotation matrix multiply with the point in the right image plus some translation vector. So then you can end up with the point in the left image. All right. So by using these equations. So if we substitute everything in, we're gonna end up with these equations that is called essential matrix, that is equal to a product of translations, which is these translations, and rotation matrix, right? This E. So okay, I can skip this. So then the question is, how do we find this E? How do we find this E? All right, this essential matrix. So the unfortunately, because we don't know this point, we don't know this point in left image, and also we don't know this point as well. Why we don't know? Because we what we know here, what we know is just inside the camera. We know the inside camera, but we don't know this point here. So that's what we don't know. Oops. So we don't know, right? But what we know is we know the corresponding point in image coordinates. We know that because we already defined the corresponding point by using zip, something like that. All right. So we don't know that. So we know the corresponding point. So then we can use that coordinates of the corresponding point to find the matrix, right? To find the camera to find the essential matrix. So if we like substitute this value known matrix of the camera, right? Because we know this intrinsic parameters over here, we know this is what we know, right? We can substitute this in this form. So finally, we gonna end up with this. Let me just skip this. So we finally end up with this form of in terms of equation. So we got what we call the fundamental matrix. So how do we estimate the fundamental matrix? All right. So how do we estimate that? So first, we know the corresponding point. And then if you look at this one, it's very familiar, or it's very similar to what we did in the finding the homography in SIF, right? So if you look at this equation, it look very similar. So you can calculate this epipolar constraint for each corresponding point. So because we know this corresponding point, so we can use these equations to write out the epipolar constraint. All right. So finally, you're going to end up with a very similar equation that is AF, right? So we have seen AH, we have seen AP, right? We have seen AP. Now we have AF, all right? So which used the same constraint of least square, okay? So yeah, we are just like solving the same equations again, having the same constraint again, and then this should look very familiar to you. That is constraint linear least square problems. So finally, after rearranging some of these steps, we're gonna end up with these equations, right? It's the same equation as the essential matrix. All right. So after that, so after we find this one, we can extract the rotation matrix and translation matrix from this essential matrix. Okay. So let me see. That's quite a lot of that. So let me just show you the end result first. So why we do this? So this is the applications of 3D reconstructions. Okay, this is a 3D reconstruction. If you look closely, this is created by capturing many image, right? Many image, and then you going through all that process. You can create a 3D structures out of that. All right. So this video is showing the results of 6,000 something image. All right, 6,000 something image, and then you stitch them together, and then calculate those matrix to find the transformation between each image. So then you can reconstruct a 3D structure. So in Panorama, what we are doing, we are stitching 2D image together, stitching in 2D plane, right? Without knowing the depth. That's Panorama. But when you are doing the uncalibrated stereo, you want to calculate the depth. So when you know the depth, you have the third dimension. When you know the depth, you know that two images, when they are stitching together, there is the Z information as well, so that you can reconstruct this sort of 3D structure by using this uncalibrated cameras structure. All right. So this is how we can reconstruct a 3D structure, or sometimes we call the point cloud. Okay, this is how the point cloud is constructed. But before we getting this result, it has to go through all the mathematics information, in mathematics operation that I show you. All right. So to create a very huge 3D structure, it requires like 1,000, 6,000, 10,000 images for this calculation to get these 3D structures of the objects. All right. So these are just the example. So to just show you what the point cloud look like after you getting it. So this is the point cloud, right? As you can see, there's a small dot over there, small dot over there. So this is so each and every point in here, the dot over here. So each dot has a coordinate of X, Y, Z, which represent the 3D coordinate of each pixel, right? It has the depth Z coordinates, X, Y, Z. So that's why we can come up with the 3D structure of that. So if we have a very dense point cloud, if you look at very from far away, it just look like the image itself. That's what they are rendering here. So for example, if you zoom in, you will see a very, very small dot. But if you zoom out, you will see like the image. All right. So that's how we can create reconstruct a 3D structure using just 2D image. But you have to find the projection between the image.
For this project, they
Mhm.
use only one camera to capture all of the image, or they use multiple cameras, because as you said originally that if we have like 20 something image, we can estimate the intrinsic parameters. So
Mhm.
yes, with this method that you discussed so far, that given that we know the intrinsic information, so if one camera is easy to estimate that. So
Yeah.
my question about this project only, do they capture by many camera or just one camera?
They capture just one cameras. So they
Oh.
capture just one camera because otherwise you have to calculate intrinsic cameras for each and every camera that you use. All right. And then there will be an errors when, so there always be an errors if you are having multiple matrix for transforming the point from one camera's coordinate to the image plane, and also another point from camera coordinates to image planes of another. So you have two camera, two image. So there's an error inside the cameras of this, and there's another errors inside the camera, these cameras. And then you want to find the transformation between the image from the two cameras. So there will be another errors, which means there will be an accumulated errors going on. But if you are using only one cameras, there will be only a single errors that will be accumulated. That is the errors that is when you're transforming from the world coordinates to these cameras, and another one will be world coordinate to this camera, but there's no errors inside the cameras because you are using the same cameras. Yeah, so for this projects, I believe they are using just single camera and then taking like this 6,000 images here. Yeah.
Yeah, that should be more easier, because if we take multiple cameras, we need to store all of the camera information of all of the so to make the calculation even
Yeah.
Yeah.
Yeah. So that's the applications of what I'm trying to convey here, that after we find some like these translations and rotations, so this will be the extrinsic parameters, right? Extrinsic camera parameters. And then we have to compute the depth, right? We have to compute the depth using these equations. I'm not going into detail, but this equation just used to find the depth, the third dimensions of those points in the image. So yeah, that's how we end up with calculating the depth of the image using this least square constraint. Yeah, I know there's a lot of mathematics, but the concept is just that. Okay. These are the step that it needs to construct this. But before we can construct it, there's a lot of mathematics going behind the scene, going on behind the scene. So if you can understand the mathematics, it just better help you dig down into what is really going on. But if you cannot handle mathematics, just understand the concept. That's how it works. That's just how it works. All right. So yeah. So you might be complaining that why this computer vision has a lot of mathematics going on, but that's it's all about, Computer vision is all about mathematics. It is not just all about the image. It's not just all about the cameras, but behind the scene image and cameras is all mathematics. All right, it's all mathematics. You have to understand. But in terms of applications, all right, so we have to separate from the foundations and application side. All right, if we're talking about the application side, you don't need to know the mathematics. You just need to know how to use OpenCV functions. All right, so that's the application side. But if you want to extend, or if you want some customized solutions, you have to understand mathematics. For example, in some applications, you are using CIF, but CIF does not solve your problems. You need to customize CIF. How can you customize CIF? Writing a Python function, writing a Python script to perform some customized CIF. So without understanding the mathematics behind CIF, you won't be able to do that. All right. So that's why I'm trying to incorporate both mathematics and the application that we have. The thing that we do in lab, that is the application side, show you how you can convert this sort of mathematics into the real applications, just applying this. But if those functions from OpenCV does not solve your problem, does not serve the thing that you want, you have to go back to the foundations, understanding the mathematics. How can I trigger this point? How can I change this point? What are the mathematics behind the scene? All right. Or for example, if you are having the applications of these robot visions, for example, if you're having these robot visions or anything that visual tracking, something like that, but the traditional or the available OpenCV function does not solve this one. You have to go back to foundations, all right? You have to go back to mathematics, tuning something, writing the Python function to do some customized features, right? So that's it. That's where it needs mathematics anyway, all right? Or even though just from my experience, all right, from my experience, we have been working with mounting the 3D sensor on the robot's hand. So what we want to do is that we want to extract the 3D information or the 3D structure. We want to reconstruct back the 3D information. So we have to place the objects inside the robot's hand that is equipped with the 3D cameras. So we want to scan these objects, and then we want to extract the 3D structure of these objects. So the basic thing that we need to do is the camera calibrations, which means that we need to understand how we can project the image from the camera coordinate back to here, back to the robot's coordinate. This is your robot's coordinate, all right? This is your robot's coordinate. This is the image or the camera coordinates, all right? So for example, you have an object over here, and then you use this camera to capture this object. So the point up here in this camera image, it is sitting in this coordinate. But the question is, how can you manipulate the robot arms to move from here to here and then capture or and then pick up these objects, which means that you need to know the point of this with respect to this robot coordinates, right? So that's what you need to know. So which means that you have to project or you have to translate this camera coordinates to this joint first. This is the first joint, and then the second joint, and then the third joint over here, and then the fourth joint over here, and then back to the robot's coordinates. So there are many projections you have to do, but without understanding this, you don't even know what is the intrinsic, how you translate from one coordinate to another coordinate. So that's why you need to back into that one. So yeah. So just to give you a briefly overview why we have a lot of mathematics, why don't we just jump right into the OpenCV function? So yeah, that's all it needs. Yeah. So you never know when you're gonna need some customized functions. Yeah, so I'm just trying to cover many things, but within the focus of within the scope of this course. All right. So any questions for today class, both morning and afternoon?
No. Need digest this calibration a lot
Yeah,
sometimes.
so yeah, there's a lot of information, so maybe you need some time to digest. I totally understand that this is the first cut maybe you're seeing this, but yeah, probably need a couple more hours to digest this. Yeah. Yeah, so if there's no questions, tomorrow we are. So from the last week and up until this class, we are mainly talking about traditional computer vision methods. Okay, so from next class, we are going to talk about a learning-based methods. So we are going to start with a machine learning for classification for image classification. So that's the first thing we are going to do. So then before we dive into another complex like object detection using YOLO, something like that, or image segmentation using U-Net. So from next class, we are switch our gear to machine learning to learning-based method in computer visions. All right. So that's for tomorrow, but for the next week, Sunday, I believe Sunday. Let me see. So as I told you that we are going to have, let me see. So we are going to have these midterm project presentations that is next Saturday afternoon, right? So just to recap here, in the mini project, you have to finish the demo, right? The demo that I give, adding functions, adding whatever function you learn from this class. All right, you learn from lecture 3 to 6 here, adding those functions into the demo. All right, so in the presentations, you have to show those features that you added, or maybe if you are like more creative, you want to add other features, or you can use AI to help you come up with other features. You're welcome to do that. So in this presentation, you have to submit two things. First, your code. All right, your code. Second, the slide. All right, presentations explaining what you are doing in this one. What are the functionality or the feature that you added to the app that you did. All right, so the code and the presentations.
So the presentation is explain the application.
Explain the application and how you do it, like
Okay.
the algorithm of that. Yeah.
Yeah, okay.
Okay.
I got.
So that's the mini projects presentation on next Saturday. All right, so tomorrow we are going to learn the machine learning for classifications. Okay, all right, and that's the tomorrow. So any questions?
My application.
Any question related to the class or the mini projects?
I from 1, 2, 3, 4. I right now I have only 4. convert to grade. I change the brightness and the contrast.
Yeah, anything you can come up with, you guys can come up with, okay?
Edge. How we do corner here? Cannot. Impossible. Can do.
Yeah, we can do. Yeah, anything, any functions that we have been discussing or we have not discussed, you can do that as well. Or today we learn another technique that is to detect a line, right? Line detections. You can do that as well, right?
Okay.
All right. If there is no questions, maybe this is it for today. I will see you tomorrow. All right.
Okay.
All
Thank
right.
you.
Bye bye. All right. Have a good night. Bye bye, everyone. Have a good night, Yi.
Yeah, thank
I'll
you.
see you tomorrow. Okay. Bye bye.
Mm.
Stay warm.
Yeah, it's
Right.
really cold.
Yeah. Okay. Yeah. Stay warm. You have a heater. Just turn on the heater. All right. I'll see you guys tomorrow. Bye bye.
See you. See you.
Hôm qua cứ bật mic lầm bầm làm thầy tưởng ông còn gì thắc mắc.
Thắc mắc lắm chứ. Quá trời thế kia. Cái này có rồi. Cái app của em rồi. Reset.
Giờ ngồi đợi cô Chutipon à?
Chắc vậy quá. Làm sao làm panorama được trời?
Anh cũng đang định làm cái đấy. Chụp 5 cái ảnh ghép lại là một.
Nhưng mà nó làm trên cái app này nè.
Ờ.
Bữa thầy demo sao quên bà.
Thầy có cấm đâu.
Biết rồi, bữa thầy em có demo mà.
Đó, thầy có demo mà, thầy chụp mấy tấm hình, thầy tự chụp trên camera. Có vậy là làm lại y chang cái demo của thầy đúng không?
Ôi làm cái gì đơn giản thôi, anh có biết có hiểu gì không?
Em thấy anh là hiểu nhất mà, anh Hoàng Anh.
Anh chịu.
Em thấy anh gật gù suốt.
Đâu anh có bật cam đâu sao em biết anh gật gù.
Đó thì em cảm thụ được anh gật gù suốt.
Gật thần giao cách cảm hay gì?
Nghe như nghe kinh thánh.
Lại nhờ kỳ này lại nhờ cô ý cho nên tiếc thôi.
Yes.
Ủa ngày mai, chiều mai phải làm cái gì nữa không? Môn cô Chitibong đó.
Chiều mai output là gì anh nhỉ? Show lại cái idea hay là show cái gì?
Chắc vậy á. Bữa có nói cô làm gì ta?
Ủa? Chiều mai hả?
Review. 9
Mình
người.
đang giữ rồi. Chưa kịp, chưa biết gì luôn. Mày lịch lộn quá chả nhớ.
15 phút, 20 phút gì đó. X detection, ok. Corner detection. Sao làm được hả? Geometry transformation.
Hello, everyone.
Hey, hello, doctor.
Your class with Dr. Chesak has already finished, right?
Yeah, we
Oh,
just
okay, sorry. Otherwise, I'm interrupting the class session anyway. So glad. How are you? How's everyone?
yeah, good.
Good. Okay. Glad to hear that. Let me see how many of us here. Not everyone. I do recall we do have session tomorrow. That's why today I would like to have some conversation because regarding the plan for tomorrow. Everyone, even your camera is not on, but you're with me, right?
Yes,
Okay.
I'm here.
Okay.
Yes, I'm here.
Okay, thank you. Thank you. I will not take long for today. I know that you've been tired with the computer vision class, perhaps. Regarding tomorrow, actually, there's the regarding our project proposal development and things, right? I would like to quickly get some update now so that I can plan tomorrow's session properly. How are things going on with everyone?
Uh, yeah, I did read something. I mean, not many things. I did put it side on the Mendeley and some summarization, but no something about what I try to the topic I read, most likely the medical segmentation. So I read a lot, some papers, have some summary. Maybe I plan to put on the most likely the review paper on that topic, and then maybe I will summarize on the slide or the now I have in the works format. Maybe put summarize a file with some picture.
Okay. As I mentioned last time that we met, even in person for some of us, and then online for many of us. Yes, I would like perhaps for these exercise things we've been working. Basically, it's for you to try to identify the problem, the area, and then doing some readings, literature review, especially especially from that time we have not learned or study the computer vision course yet. So there's still some possible areas that you might want to explore regarding computer vision, right? So that's why I would like to sense as of now that maybe those who have very clear and a firm idea regarding the topics that you would like to work as your project, then of course you are encouraged, or you can go ahead with your firm idea. But those who still need a bit time to explore a bit, that's still fine, but not too long. Because then, yes, it may, I mean, not too long in the sense, it's just the concern of completing your study within the plan. That's the only thing. But if you are fine to delay a bit, that's also fine, okay? But if not, of course, we may need to have some fixed timeline, deadline, or milestone. All right, that's the only thing. But as for tomorrow's session, actually, last time I have not engaged or introduced to you a TA for this course, or those some of my I am engaging. I have engaged a PhD student under my supervision to perhaps help or assist that, not really help in order to work, right? It's gonna be all your work, but assisting, supporting, or giving some feedback in case you may want to discuss or get some ideas from several people. Then that's one thing that I would like to inform. So first, yes, I would like to introduce and inform that there will be a TA. We have already set up the TEAL. Last time I did not properly share the materials to all of you through our TEAL system, right? But we already did, but we will communicate to you. And third, some of the tools or things that may help you, we learn manually. We learn, of course, the techniques, the process, but there will be Scopus 2, Scopus AI, and also something that could help you search and analyze the trend of research properly as well. My TA, he will be introducing and sharing, demonstrating and guiding you through this tool tomorrow as well. Okay, that will be the thing that will happen for sure. Okay, and I hope that this will help you further for those who are new to these things as well. And regarding your project proposal and problem topic identification and literature review, actually the key assignment, right? I would like to, I think maybe it's important to have, maybe individual meetings sometimes, or for me to go through some of your review, your ideas so that I can review, because sometimes it's kind of whole class discussion, and maybe some of you have shared, some of you may not have a chance to yet share or discuss with me. Then I would like to encourage the very first thing. Discussion is fine. Meeting, individual meeting or small group meeting is fine, either with me or either with a TA. But before reaching that state, I believe that sometimes it's good for you to write something. Even it's a broken English, but at least it's a way to express your idea and interest. It doesn't need to be a proper research report or document, but sometimes when it comes to to talking alone, things disappear. Only in the conversation, right? Like this. If I don't give you proper slides, materials, and I just keep talking alone, I believe that sometimes things are not properly tracked, or sometimes you need to read and analyze and spend some time. And the same for me. I would like to encourage everyone in the team. There will be a submission for a draft, the initial idea. I encourage everyone to submit whatever you have, so that at least I can hear or see something from that submission. And I can perhaps comment or give some idea back. And when we have a face-to-face meeting, either online, then I have something that I can look into, right? Otherwise, it's just a memory that I have to recall that, oh yeah, I used to speak with Mr. Kwa, I used to speak with Mr. Kwang, I used to speak with this and that, and then I just recall and refer to my note, right? I don't think that proper. That will not be effective if I rely on just my note. So tomorrow, I'm very sorry that I may not be able to be with you during the afternoon session, but my TA, his name is Su Hel. I will write an email after, today, introducing you and summarize everything we discussed today, so that we have something to refer to. And whether I also will insist that I need your actions, such as summarize to me your idea, your thing, or submit to me whatever you have so far that you think is good for me to know your status as of now. And it's good for you to get my feedback or something, okay? But yes, my student, you can talk to him for anything regarding the project, the idea, or even just kind of, sometimes even it's not solid yet, right? But you may want someone for you to explain your idea, and you want some feedback or some questions for you to think further. At this stage, sometimes it's like that as well. You want someone to give you questions so that, oh yeah, why not? I never thought of that way, something like that. Okay. Do you think it will be possible if we plan it this way?
Yes,
Yeah.
thank you, Professor.
Yes.
Very clear.
Okay.
But I
And,
encourage. Yes, sorry. Again, please, Mr. An.
yes, as you mentioned last time, at the tomorrow Sunday, we have to present the chapter 1 introduction and chapter 2 literature review. At the chapter 1, we have to show you the important thing is the state of the problem, the research question.
Yes.
Yes, and at the chapter 2, we have to show the solution to solve the problem, right?
Yes. Actually, that if you can make it, I mean, you have prepared for that. I may not be able to connect online to listen to you live, but you first please submit what you have prepared. I will comment for sure. I will read and go through. Second, for those who are ready, I will come. You please communicate to me. We can have some kind of separate or additional meeting. It may be separate, it may be a group, I don't mind, but maybe some of you, sometimes you may want some private meeting, or some of you may have not may not be available during the same schedule, I mean, right? But I don't mind either a separate meeting or either a group meeting, so that we learn from each other. That will be also good. But maybe a short separate meetings, that could be a good idea, and then a kind of group meeting that we learn from each other idea, that also good as well, right? Yeah. I do encourage a group meeting so that we learn the idea from others. We learn the project techniques from one another, and we help each other kind of collectively too. That is always the effective mechanism.
Okay.
Okay. So as for tomorrow, you will have Dr. Shursak class until 12, I guess. Am I correct? It's
Yes.
still confirmed, right? So what time you want to start this afternoon session to learn about Scopus AI and a few other things, and perhaps you can at least even those of you who want to share, present, or get some quick feedback among yourself or with the TA is also possible too. Should we start as
1
planned at
p.m.
1
is
o'clock?
okay. Yes.
Okay,
1 p.m.
1
is
p.m.
okay.
Confirmed, yes. Good for everyone, right?
And if I have many idea, can you recommend that
Yes.
I can choose one?
Yes.
That's not so complicated.
Fine, no problem. I can
Okay.
give some comments on several ideas.
Yes.
Yes.
Thank you, Professor.
Thank you, everyone. And others, do you have other comments or other things? I mean, other classmates, other students? Mr. Viet, Mr. Nam, Mr. Nam. Okay, if
Okay,
not,
I'm back.
okay, if not, let's confirm to meet at 1 o'clock tomorrow, but also please submit. It can be after tomorrow session as well, if you still want sometimes to revise a few things, okay? Okay.
Okay.
And yes, Mr. Hung. Okay. So if nothing, then we can finish our session as of now. But seems like Mr. Hung would like to spend a few minutes. Then I stay a bit more minutes. And then if somebody else want conversation, private conversation, individual conversation, whatever, I stay a bit longer.